On a clear night in autumn, when the air has gone cold enough to sharpen every point of light in the sky, there is a star in the constellation of Cetus that may or may not be there. Some nights it stands clearly visible, a warm and ruddy point low in the south, unremarkable among the other stars but present, definite, something the eye can find and return to. Other nights it is gone, not obscured by cloud, not drowned in the light of the moon, simply absent, faded below the threshold of what the eye can catch, retreated into a darkness so complete that even a careful observer scanning that region of sky would find nothing where the star had been. And then, over the following weeks, it returns, slowly, one magnitude at a time, brightening so gradually that no single night shows a clear change. The star accumulates light across days and weeks until it stands as one of the more prominent objects in that part of the sky. Then the long, slow withdrawal begins again. The star has been doing this for longer than anyone has been watching. It will keep doing it long after all watching has stopped. The act of noticing requires a particular kind of patience, not the patient waiting for a specific event, an eclipse, a meteor, the transit of a planet, but the patient willingness to look at the same thing on many separate nights, remembering what it looked like the last time, holding that memory against what is visible now, and being honest about the small and quiet differences. Most stars do not reward this kind of attention. Most stars simply burn, steady and consistent, night after night, year after year, giving no sign that anything inside them is changing. A careful eye surveying the sky will find the familiar stars in their familiar brightnesses, the sky reproduced so precisely from one winter to the next that the resemblance feels absolute, as if the sky were a fixed and finished thing, but it is not, and the signs of its slow motion are there, for anyone willing to look with enough patience to catch them. A star that changes its brightness over time is called a variable star. The definition is plain, and the phenomenon is common. Roughly 1 in 30 of the stars visible on a clear night from a dark site shows some form of measurable variability, and among the stars too faint for the naked eye, the fraction is higher still. The change is measured in magnitudes, an old astronomical unit inherited from the Greek astronomer Hipparchus, who ranked the stars in the sky from 1 to 6 by how bright they appeared to the eye. The scale runs counterintuitively. Lower numbers mean brighter stars. A star of magnitude 1 is roughly 2.5 times brighter than a star of magnitude 2, and a star of magnitude 0 is brighter still. The full difference between the faintest star the naked eye can detect on a perfect night and the brightest star in the sky spans a range of about 6 magnitudes, which corresponds to a factor of roughly 250 in actual light received at the eye. A variable star may change by a small fraction of a magnitude, a shift so subtle that only a careful instrument would catch it, or it may swing across several magnitudes, rising from near invisibility to a brightness that commands the sky. Some stars change between these extremes over days. Some take months, some take years, and the mechanism that drives the change varies from star to star as widely as the change itself. The first question an astronomer asks of a variable star is whether the variability comes from inside the star or from outside it. This distinction cuts through the enormous variety of variable stars and sorts them into 2 fundamental categories. In one, the star genuinely changes. Its surface rises and falls, its temperature shifts, its luminosity grows and fades as something physical happens in its interior or in its atmosphere. These are called intrinsic variables. In the other, the star itself is perfectly constant, burning as steadily as any ordinary star, but something about its geometry, the presence of another star passing across its face, or a dark spot rotating into view, makes it appear to brighten and dim from where the observer stands. These are called extrinsic variables. The light changes, the star does not. Inside the broad category of intrinsic variables, the mechanisms are many. A star may pulsate, its entire outer envelope expanding outward over days or weeks, then contracting back, then expanding again, the surface rising and falling like the slow breathing of something very large and very old. It may erupt, building up material on its surface or in its interior until a threshold is crossed and energy is released suddenly, blasting light into the surrounding space. It may flare, its magnetic field twisting and reconnecting in a burst of energy so brief that it is finished before most instruments can complete a single measurement. Or it may simply be in a phase of its life when it is too massive and too luminous to exist in a single stable state, oscillating between competing equilibria over long periods. Each of these mechanisms leaves a different mark on the way the star's brightness changes over time, a different pattern, a different period, a different shape to the brightening and the fading, and that pattern is the primary tool astronomers use to understand what is actually happening inside the star. The record of a star's brightness over time is called a light curve. It is exactly what the name suggests, a graph, with time running along one axis and brightness and magnitudes along the other, each observation plotted as a single point, and the points connected or smoothed into a line that traces the star's behavior over the period of observation. The shape of that line carries more information than the numbers alone suggest. A light curve that is smooth and sinusoidal, a gentle repeating wave, tells one story. A light curve that rises sharply to maximum brightness and then descends more slowly, like the steep leading edge of a wave and its long trailing slope, tells another. A light curve punctuated by sudden vertical drops, flat intervals of constant brightness, interrupted by sharp, brief dimmings that come and go at perfectly regular intervals, tells a third. The curve is not merely a record, it is a portrait of the mechanism. Reading it requires the same kind of patient attention that noticing the variability in the first place required, not a glance, but a long, quiet observation that takes the whole shape into account. The earliest systematic observations of variable stars were made without any of the tools now used to produce light curves. There were no photometers, no photographic plates, no CCD detectors. There was only the eye, the naked eye, or the eye at the eyepiece of a small telescope, comparing the brightness of one star to another on the same night, estimating a magnitude by placing the variable between two reference stars of known brightness and judging where it fell between them. The estimates were not precise. Nights varied in transparency, eyes varied in sensitivity, but repeated over many nights across many years by observers who were patient and careful and honest about what they saw, the estimates accumulated into something real, a record of brightness over time that, even in its imprecision, revealed the underlying pattern. It was in September of 1596 that the Dutch astronomer David Fabricius first recorded the variability of the star, now known as Omicron Ceti. He was using the star as a reference point for observing a nearby planet, and he noted that it was distinctly visible, third magnitude, by his estimate, bright enough to use without difficulty. When he returned to the same region of sky, some months later, the star was gone. He could find no trace of it where it had been. And then, in the following year, a report from another observer placed it back in the sky, brightening again. Fabricius did not fully understand what he had seen. He took the star's disappearance to be caused by an eclipse of some kind, the blocking of its light by some dark companion, and the reappearance to be the eclipse ending. He was wrong about the mechanism, as it happens, but the observation itself was careful and true, and it stands as the earliest confirmed record in Western astronomy of a star that changes its brightness over time, a star that was there, and then was not, and then was there again. For the next century and a half, the collection of known variable stars grew slowly, one or two at a time, noticed by observers who happened to be watching the right region of sky on the right night, and who were attentive enough to recognize that what they were seeing did not match what the charts told them to expect. The work required no special equipment and no formal training. It required only a clear sky, a good eye, and the willingness to keep records. And because it required so little beyond patience and care, it attracted observers from outside the professional world of astronomy, amateurs in the truest sense, people who watched the sky because the sky held their attention, and who recorded what they saw because recording seemed the natural thing to do with an observation. It was one of these careful amateurs who made the next great step in the study of variable stars, and the circumstances of his observation are worth dwelling on. John Goodricke was born in 1764 in Groningen, in the Netherlands, into an English family. He was deaf from childhood, possibly as a result of an early illness, and had grown up in a world where most ordinary forms of communication were partially or wholly closed to him. He had been educated at a school in Edinburgh that specialized in teaching deaf children, and he had come through that education with, among other things, a clear and methodical habit of thought and a deep interest in the natural world. He moved to York in his teens, and it was there, in the cold autumn and winter of 1782 and 1783, that he turned his telescope on Algol, a star in Perseus that had been noticed to vary in brightness as long ago as the 1660s, but had never been systematically studied. What Goodricke saw over the following months was not the vague, slow variability of a star like Omicron Ceti, shifting over hundreds of days. Algol dimmed and brightened on a period of just under 3 days, quickly enough that a patient observer could detect the change within a single evening. The dimming was sharp and deep, a drop of more than a full magnitude in brightness, and it returned with an almost clock-like precision, the same depth and the same duration every time. Goodricke timed the dips with care, night after night, adjusting his estimates against the steadier reference stars nearby. The pattern that emerged from those nightly records was crisp and unmistakable. Algol was not slowly oscillating in some internal rhythm. Something was blocking its light at perfectly regular intervals. The hypothesis Goodricke proposed was that a dark companion body, a star that did not itself glow, or a planet of sufficient size, was orbiting Algol and periodically passing across its face as seen from Earth, blocking some of the star's light for the duration of each transit. The idea was speculative in a period when no one had yet confirmed any kind of stellar system beyond the solar system, but it fit the observations perfectly. The period was exact, the duration of the dimming was consistent, the depth of each minimum was the same. Only an eclipse, a geometric event caused by the orbital motion of one body around another, could account for such regularity. The brightness did not change because the star itself was changing. It changed because a dark companion was periodically standing between the star and the Earth. Goodricke was right, though the companion turned out not to be a dark body, but a genuinely luminous star, orange and cooler, and less bright than Algol itself, orbiting so closely that its revolution around the primary star took just under 3 days. When the cool companion crosses the face of the brighter star, the light the system sends toward Earth drops sharply. When the brighter star crosses in front of the cooler companion, there is a smaller and shallower secondary minimum, just detectable in a careful light curve. The pattern is perfectly regular because orbital mechanics is perfectly regular. The two stars circle each other without interruption in a plane that happens to be aligned closely enough with our line of sight that each transit crosses the face of the other. Goodrich could not have seen all of this from his position in York in 1782, but he saw enough to propose the right idea, and the right idea was confirmed by later, more powerful observations across the centuries that followed. In the same year that he was working through the Algol observations, Goodrich turned his attention to another star in a different constellation, Delta Cephei, in the constellation of Cepheus, near the north celestial pole, had not previously been recognized as variable. It had simply sat in the sky, a faint but visible point, undisturbing and apparently steady. Goodrich looked at it again and again across the autumn and winter of 1784, comparing its brightness, night by night, against the stars nearby, and what he found was a variation with a period of 5 1/3 days, a smooth asymmetric wave that rose from minimum to maximum quickly and then fell more slowly back to minimum. Not the sharp regular dip of an eclipse, something different, something gradual. He proposed that this variation too might be caused by the eclipse of a companion body, but the shape of the light curve was wrong for that explanation. An eclipse produces a flat-bottomed minimum, a sharp drop and a sharp recovery, with flat stretches of constant light in between. Delta Cephei showed no flat stretches. Its brightness changed continuously throughout the cycle, rising and falling in one smooth curve without interruption. This was not an eclipse, but what it was, Goodrich could not say with certainty, and he died in 1786 at the age of 21, before the question could be resolved. He had been elected to the Royal Society the same year, an honor that reached him only weeks before his death. The cause was never established with certainty, but exposure during his many long nights of winter observation may have contributed. Delta Cephei was not an eclipsing system. The star was pulsating, its outer envelope rising and falling in a cycle that would later be understood in detail, the star itself expanding and contracting on a period of 5 1/3 days, brightening as it contracted and the photosphere heated, fading as it expanded and the outer layers cooled. The mechanism was entirely internal, a property of the star's own structure rather than any external geometry, and it would eventually be found to connect the period of pulsation to the star's intrinsic luminosity in a relationship that became one of the most powerful tools in all of astronomy for measuring distances across the universe. But that application would not be discovered for more than a century, and the pulsation mechanism itself would take even longer to understand. What mattered in 1784 was the light curve, smooth, periodic, asymmetric, repeating with clock-like fidelity from one cycle to the next. The shape was information. The shape was a record of something happening inside the star, though the language in which that record was written would take time to learn. The decades and centuries that followed brought more variable stars and more systematic ways of recording them. Individual observers with small telescopes and careful eyes continued to add to the catalogs, reporting new variables, refining the periods of known ones, building up the records that would eventually become the long, unbroken light curves that span more than a century of continuous observation. And in the late 19th century, the advent of photography transformed the work entirely. Before photography, every observation of a variable star required a human eye at a telescope eyepiece, making a judgment by comparison and writing it in a notebook by lantern light. Each observation was a single point, separated from the last by a full night or many nights, the gaps between points sometimes weeks or months, depending on the weather and the observer's schedule. The precision was limited by the eye's ability to judge small differences in brightness, by the consistency of atmospheric conditions, by the steadiness of the observer's attention. Good observers working under good skies could achieve precision of a few tenths of a magnitude, which was sufficient to track the broad outlines of variability in the brighter stars. But subtler variations, changes of a few hundredths of a magnitude, were beyond reach. Photography changed everything about the scale of the enterprise without changing its fundamental method. A glass plate coated with a light-sensitive emulsion, exposed for several minutes under a telescope, recorded not one star, but hundreds or thousands at once, the images of each star appearing as a small black dot, whose size and density encoded its brightness. A plate taken of one region of sky could be compared directly to another plate taken of the same region months or years later, the sizes of the dots compared by eye or by an instrument called a blink comparator, which switched rapidly between the two images, so that a star that had changed in brightness between the two exposures would appear to flash or wink as the images alternated. Any star that varied between the two plates would give itself away immediately, its dot changing size, while all the steady stars around it remained the same. The systematic sky surveys of the late 19th century produced archives of glass plates, thousands of plates, each covering a patch of sky, laid in wooden drawers in the basements of observatories and preserved across decades. The Harvard College Observatory accumulated one of the largest such collections, hundreds of thousands of plates covering the whole sky over periods stretching from the 1880s into the 20th century. Women hired to examine and classify the images on those plates. Astronomers in all but the formal recognition the era was willing to extend to them, worked through the Chepchengar and risk methodically, comparing plates, cataloging new variables, measuring brightnesses, and recording them in ledgers that would eventually become the raw data for some of the most important discoveries in the history of astronomy. The plates themselves were small, a few inches square, each one representing a small region of sky on a single night. Laid side by side, plates of the same region taken months apart, the tiny dots that marked the stars shifted almost imperceptibly in size, the changes so small that only careful measurement could confirm them. But the changes were there. The sky, examined with sufficient patience and recorded with sufficient care, was not still. The work was slow and meticulous and not particularly dramatic. A researcher spending a long day comparing plates was not watching anything happen. The variability recorded in the archive had already happened, months or years ago, when the plate was exposed. What the researcher was doing was reading a record, a historical document written in light, deposited on glass, and waiting to be decoded. The method required the same patience as the original nightly observation, not the patience of waiting for a single definitive event, but the patience of working through many small measurements, letting the pattern accumulate, trusting that the pattern would eventually become clear. It always did. Given enough plates and enough care, the sky was keeping its own records, and the records were recoverable. The light curve that emerged from a long series of such measurements was a different kind of object than the handful of data points a single observer could produce in a season of nightly watching, spanning years or decade, built from observations made under different skies by different instruments and different hands. It carried within it not just the period and the amplitude of the variation, but its long-term behavior, whether the period was drifting over time, whether the amplitude was growing or shrinking, whether the same pattern repeated exactly from one cycle to the next, or shifted slightly in ways that carried their own information. The long baseline light curve was not merely more data, it was a different kind of portrait, drawn with enough resolution to reveal not just the basic behavior of a variable star, but the changes in that behavior over years, the slow evolution of something that had previously appeared static. The star in Cetus that Fabricius had first noticed in 1596, the one that appeared and faded over months, received a name in 1662. The astronomer Johannes Hevelius called it Mira, from the Latin for wonderful. The name acknowledged what centuries of observation had made clear, that this was not an ordinary star doing an ordinary thing. Mira brightened from below the threshold of the naked eye to a brightness that could make it one of the more conspicuous objects in that part of the sky, and it did this on a period of roughly 330 days, a period so long that tracking a single complete cycle required nearly a year of attentive observation. The amplitude of that brightening was extraordinary. At its faintest, the star was hundreds of times less luminous as seen from Earth than at its brightest, a range that translated in real physical terms to a factor of roughly 1,500 in actual light output, the star genuinely producing 1,500 times more light at maximum than at minimum. Nothing about its appearance at minimum suggested this was coming. It sat there in the sky, an unremarkable faint smudge at the edge of naked eye visibility, and then slowly, over months, it gathered itself into something bright and distinctive and unmistakable, before slowly retreating again. What was happening inside Mira, and inside the class of stars that bear its name, would not be understood until the 20th century, when the tools of stellar physics had advanced far enough to model the interior of a red giant star in its later evolutionary phases. But the light curve, the long, slow, slightly uneven wave traced by centuries of observation, was there long before the understanding, a record of something genuine and recurring, a measurement waiting for its interpretation. The measurement came first. The meaning came later. That is often how it works. And this inversion, the record first, the understanding after, is part of what makes variable stars worth dwelling on, worth looking at again and again across a long life of watching the sky. The light curve is not a readout of something already fully explained. It is a question rendered in the language of brightness and time, asked repeatedly over years, patiently awaiting an answer that may require new instruments, or new physics, or new methods that have not yet been invented. The astronomer who draws the 1,000th point on a light curve that has been accumulating for a century is not repeating a finished task. The observation still matters, the record still grows, and the patterns that emerge from a long enough baseline continue to surprise the people who study them. The range of what a variable star can express within a single number, the amplitude, the difference in magnitudes between its brightest and faintest states, spans more of the sky than it might seem. A star that varies by one magnitude becomes roughly 2.5 times brighter at maximum than at minimum, a change that even a casual observer who knew the sky well might notice over time without any instruments. A star that varies by 3 magnitudes becomes some 16 times brighter at maximum, a change dramatic enough that an observer who had learned the sky's familiar landmarks in summer would return in autumn and find a bright star where none had seemed to be. A star that varies by 6 or 7 magnitudes, as Mira can, in exceptional cycles, rises from a point invisible to the naked eye, and reaches a brightness at which it stands out clearly against the surrounding field, a newcomer in what had seemed a known and finished sky. The experience of watching such a star, through many nights and many months is unlike the experience of watching any other class of astronomical phenomena. It asks for time, it asks for return. It rewards neither the impatient glance nor the single definitive observation, but only the long accumulating series of visits, each adding one point to a curve that only shows its shape when viewed as a whole. That curve, drawn over enough time, becomes something close to a biography of the star, or at least of its outer behavior, the visible surface of a life whose interior is inferred rather than seen. The shape of the rise and fall carries information about the mechanism that drives the change. The regularity or irregularity of the period carries information about whether a single rhythm dominates the star's interior or several rhythms compete. The way the amplitude grows or shrinks across many cycles carries information about whether the star is stable in its current phase or slowly shifting toward a different behavior. And the long-term drift of the period itself, almost too slow to catch in a single observer's lifetime, carries information about the star's evolution, the slow internal restructuring of a body that has been burning for millions or billions of years and is gradually becoming something different from what it was. A single night of looking reveals none of this, and a single season of careful observation reveals the period and the rough amplitude enough to confirm that the star is variable and to place it tentatively among others of its kind. But the full portrait requires a long baseline, and the long baseline requires patience of a kind that exceeds any single observer's career. The light curves of the best studied variable stars are built from the work of many people across many generations, observers who never met each other, but whose observations, converted to the same scale and laid in sequence, form a single unbroken record stretching backward toward Fabricius and Goodricke and forward into the present night. There is something steadying in this, the idea that a measurement made carefully on a clear night in York in 1782 still belongs to the same record as a measurement made tonight by a robotic telescope sweeping the sky automatically. The observations are separated by more than 2 centuries, made by people and instruments with almost nothing in common except the star they were looking at and the care with which they looked. But the light curve holds them together. It treats a human eye and a digital sensor equally as long as the measurement is honest and the magnitude is correct. The graph is indifferent to who made the point. It cares only about the brightness and the time. In the quiet of a dark observatory on an autumn night, the graph is not much to look at. It is a series of points on a page, or now more often on a screen, connected by a smooth line that a person who has spent years studying it can read as readily as a sentence. The line rises, the line falls. In a simple case, a cepheid, a classical variable with a clean and regular light curve, the shape repeats almost identically from one cycle to the next, from one cycle to the next, a wave so consistent that covering part of the curve and showing it to a physicist who knows how to read it will let them describe the hidden portion without ever having seen it. In a more complex case, a semi-regular variable in which several pulsation modes interfere with each other, the curve is less predictable, the period wandering, the amplitude shifting, the pattern almost but never quite the same, from one maximum to the next. The complexity of the curve reflects the complexity of the interior from which it comes. But in either case, the clean wave or the wandering one, the curve represents something real that happened inside a physical object hundreds or thousands of light years away. Every dip and rise in that line is a record of energy, energy released, energy stored, energy ascending through layers of ionized gas and escaping at last as light that crossed interstellar space and arrived, on some numbered night, at an instrument small enough to fit in a building and sensitive enough to notice the difference between one magnitude and another. The instrument did not know it was participating in something that began in 1596. The light did not know it had been traveling for hundreds of years, but the graph knows in its own way, and the graph is complete enough to last. Far above a dark field where no artificial light disturbs the sky, the star in Cetus hangs where it has always hung. On a night when it is at or near its maximum, it is one of the more conspicuous objects in that region of the southern sky, its orange color perceptible even to the naked eye, its presence easy and obvious. Someone who looked at the same field 3 months ago and found nothing would now find this. The difference is not in the sky as a whole, which is the same vast dark field it was before. The difference is in this one point of light, which has been doing something that requires a long baseline to fully appreciate. It has been moving toward the eye slowly, across months, from a brightness too faint to reach the naked eye, to a brightness that needs no instrument. And when it reaches its peak, it will begin the long, slow withdrawal again, fading across the following months as gradually as it brightened, retreating back into the dark until the next cycle brings it forward again. Somewhere in a drawer of an observatory or in a database of measured magnitudes that spans more than a century of nights, the record of this motion is preserved. It is a curve drawn not in a single sitting, but across generations of patient watching, a line that rises and falls and rises again, its shape slightly different from one cycle to the next, its period drifting almost imperceptibly over decades, its full length representing more time than any single observer has been alive to watch it. Every point on that line was placed there by someone who looked up at a dark sky and noticed with quiet attention that the star was not quite the same brightness as the night before. The noticing required nothing special, only a clear sky and patience and the willingness to return. That line, drawn across years of careful looking, holds more than measurements. It holds the inner life of a star, not as something extracted or translated, but as something recorded in the only language the star speaks across such distances, light and time and change. The graph continues to grow, the star continues to breathe, and somewhere in the darkness, both of them persist, as they have persisted, quiet and unhurried and entirely indifferent to whether anyone is watching. The outer layers of a Cepheid star are moving right now, not drifting in the slow, figurative sense that all things in space are said to drift, actually moving, rising outward over the course of days, the way a chest rises when a breath is drawn very slowly and held. The star's radius grows. Its surface cools a little as the gas expands and thins. Then, over more days, it falls back, compressing, warming, brightening toward the peak that will come just before the contraction ends. The whole cycle, rise, cool, contract, brighten, rise again, repeats with a steadiness that once measured almost never falters. To stand at a distance from such a star and simply watch is to see something that behaves less like burning gas and more like a living thing holding a rhythm. The brightness climbs steeply. It falls more slowly, a long gentle slope back to minimum. Then it climbs again. The curve drawn by this motion, plotted in light over days or weeks, has a shape as recognizable as a signature, sharply asymmetric, rising fast and falling slow. The same shape repeating with a fidelity that took the astronomers who first measured it some time to fully trust. This kind of star is called a Cepheid variable, and the name comes from the constellation Perseus's neighbor Cepheids, where one of the first confirmed members of the class was found and carefully timed. But the physical character of a Cephid is more important than the name. These are yellow supergiants, stars that have left behind the long, stable middle period of their lives, expanded outward, and now find themselves in a region of temperature and pressure where something internal has taken hold of them and will not let them be still. Their pulsation periods range from about a single day to roughly 100 days. Most of what a Cephid does in its life, it does quietly, invisibly, inside the machinery of the gas that makes it up. The breathing is all that shows from outside. There are other stars that breathe too, on shorter cycles. A class of older, lower mass pulsating stars can be found gathered in the ancient spherical clusters that orbit the outer regions of the galaxy. Each cluster a dense ball of hundreds of thousands of stars, some of them nearly as old as the universe itself. Within those clusters, if one watches carefully across many nights, certain stars reveal themselves as variable. They brighten and fade on cycles shorter than a single day, some completing a full pulsation in as little as a few hours, others taking most of a day to pass through one cycle. These stars are called RR-Lyrae variables, after a bright example in the constellation of the Lyre. Their periods are short, their amplitudes are modest. But one property sets them apart from almost every other variable: the intrinsic luminosity of an RR-Lyrae star. The actual amount of light it pours into space is nearly the same from one member of the class to the next. The brightness they reach at peak, the true brightness, rather than how they appear from different distances, clusters around 40 to 50 times the light output of the sun. Most RR-Lyrae stars, wherever they are found, glow at approximately the same candle power. This makes them useful in ways beyond the pulsation itself, but that application is a separate story. What matters here is simply the rhythm. Hour after hour, night after night, stars inside those ancient clusters brightening and fading on their individual clocks, too slow to watch over the course of one evening, but measurable across weeks of patient observation. A globular cluster seen through a large telescope is one of the quieter, spectacular things the night sky offers. The outer edges resolve into individual points. The inner regions blur together into a soft glow that no telescope fully separates into single stars because they are simply too close and too many. The RR-Lyrae stars within it are scattered through the cluster's volume, not concentrated at the center or the edge, simply present wherever they happen to be, and they carry no mark that distinguishes them visually from their neighbors on any given night. Only time reveals them. Photograph of the cluster taken on one night and compared to a photograph taken several nights later will show a handful of stars that have clearly changed their brightness. Those are the variables. On the long time scale of the cluster's life, those stars are near the end of a particular phase, having burned through most of their initial hydrogen and arrived at a condition where the interior structure is exactly right to sustain a steady pulsation. They are brief in this phase. Cosmically speaking, they will move on. But for now, they beat out their short cycles inside the old light of the cluster, steady as anything in the sky. Now consider a different kind of star entirely. Smaller than a Cephid, lighter in mass, closer in nature to the sun than to a supergiant. Delta Scuti stars are ordinary by some measures. They sit on or near the main sequence, that long diagonal band that contains the majority of stars in any given galaxy, stars that are in the long middle phase of hydrogen burning at their cores. In mass, they range from perhaps 1.5 to 2.5 times the mass of the sun. In temperature, they run a little hotter than the sun, falling in the range of stars whose surfaces glow white to pale yellow. They pulsate, but their pulsations are not the clean single-mode breathing of a Cepheid. A Delta Scorti star is oscillating in several modes at once. The outer layers are not simply expanding and contracting as a unified shell. They are doing something closer to what a bell does when struck, vibrating in complex overlapping patterns, different regions of the star moving in and out with different periods simultaneously. The total brightness at any given moment being the sum of all those contributions added and subtracted against each other. The periods of these overlapping oscillations run from a few minutes at the short end to several hours at the long end. Their amplitudes, the size of the brightness changes, are modest. In some Delta Scuti stars, the variation is so small that it was not measurable at all until satellites began doing photometry from above the blurring influence of the atmosphere. The light curve of such a star, when recorded at high precision, does not show a smooth repeating wave. It shows something irregular, with multiple humps and dips per cycle, its pattern shifting slightly from one night to the next as the different oscillation modes drift in and out of phase with each other. Mathematicians have a technique for pulling apart a complex signal like this into its component frequencies, a decomposition that reveals each individual oscillation and its strength, the way one might separate the voices in a chord by listening very carefully to each pitch in turn. Applied to a Delta Scuti star's light curve, this analysis can reveal not just that the star is pulsating, but in exactly how many ways, and at what rates, and how those rates are related to each other. From that information, it is possible to draw inferences about the interior of the star that no other method could provide: the density gradient inside, the boundary between the convective and radiative regions, the composition of the deep layers. The star's surface is the only thing any telescope can see, but the oscillations carry information up from inside, the way tremors on the ground carry information about the rock beneath. The fact that stars can reveal their internal structure through the mathematics of their surface vibrations is one of the quieter achievements of modern astronomy. It was not obvious in advance that it would be possible. Stars are opaque, no light from their cores reaches us directly. The interior of a star is as inaccessible to direct observation as the interior of any solid body. More so, because the temperatures and pressures involved destroy everything that might enter. But a pulsating star is doing something analogous to what the Earth does when struck by an earthquake. The waves that travel through its body and emerge at the surface carry a record of what they pass through. For stars, the surface brightness variations are those waves made visible, and their careful analysis has opened a way of studying what cannot otherwise be reached. There are also stars at the hot, massive end of the main sequence that pulsate, not because of helium behaving unusually, but because of something happening in a thin region of their envelopes where iron and nearby elements absorb light in ways that set a rhythm going. These are beta Cephei stars, named for the prototype in the constellation of Cepheus, the same northern constellation that gave its name to the Cepheids, though the two classes have nothing in common beyond the sky region where early examples were cataloged. A beta Cephei star carries 7 to 20 times the mass of the Sun. Its surface burns at tens of thousands of Kelvin. It is the kind of star that in an ordinary photograph of a star field shines blue-white, noticeably different in color from the yellow and orange stars nearby. It is also among the shorter-lived stars in the galaxy. Massive stars burn their fuel fast, and these will not last long by stellar standards. Their pulsation periods are very short, measured in hours rather than days, some completing a full cycle in under 3 hours. The cycles are so brief that a patient observer, staying at the eyepiece through a long dark night, could detect the brightness change directly, watching the star climb and fall and climb again before dawn. The mechanism in a beta Cephei star operates in a very different temperature zone than the one responsible for driving Cepheid pulsations. The distinction matters because it means pulsation is not a single mechanism that one class of stars happens to undergo. It is a family of mechanisms operating on different elements at different depths in different kinds of stars, each one triggered when the internal conditions happen to put the right layer of material at the right temperature to store and release radiation in the right way. Hot stars have their driver, cool yellow supergiants have theirs. Old low-mass stars circling in globular clusters have yet another. The diversity of pulsating variables in the sky is not a coincidence. It is the natural result of how many different ways a star can find itself in a condition where its own internal structure begins to ring. Deep inside a Cepheid, or an RR Lyrae star, at a depth where the temperature reaches about 40,000 Kelvin, there is a shell of material doing something that seems counterintuitive. When most substances are compressed, they become more transparent. The particles are forced closer together, but their ability to absorb light does not increase proportionally. At this particular temperature, however, helium is in the process of losing its second electron. This is the second helium ionization zone. The helium here is giving up a bound electron under the influence of high temperatures, shifting from a singly ionized state to a fully ionized one. And in this zone, something different happens when the gas is compressed. Instead of becoming more transparent, it becomes more opaque. It absorbs more radiation. It traps more heat. The layer's response to being squeezed is not to let the light through, it is to hold it. This matters because a star's internal energy is constantly trying to flow outward. Heat generated at the core moves in all directions, working its way toward the surface by a long, slow process of absorption and re-emission that takes so long in some stars that a photon produced at the center might spend 100,000 years wandering outward before it finally escapes. Along that outward path, if there is a layer that traps the energy rather than letting it pass, the layer acts like a valve. Energy is held beneath it, building pressure, and eventually the pressure pushes the layers above outward. The star expands. As it expands, the helium ionization zone cools, and the ionization reverses. The helium recaptures its electron, the opacity drops, and the layer becomes transparent again. The energy stored beneath it floods through. The pressure drops. Gravity pulls the outer layers back inward. They compress. The helium ionizes again. The opacity rises, and the cycle begins once more. This is the kappa mechanism. The word kappa refers to the opacity of stellar material, how resistant to the flow of radiation a given layer of gas happens to be. And the kappa mechanism is simply the name for what happens when a layer's opacity increases under compression rather than decreasing, creating the conditions for a self-sustaining thermodynamic cycle. The layers above the ionization zone are driven outward, allowed to fall, driven outward again in a rhythm set by the physical properties of the gas and the depth of the driving zone. The period of the pulsation, the time it takes the star to complete one cycle, depends on the star's size and the speed at which pressure waves can travel through its interior. Larger, more luminous stars take longer to complete each cycle. This relationship between size and period is not arbitrary. It is a direct consequence of the physics governing how waves move through gas, and it is as regular as the relationship between the length of a pendulum and the time of its swing. The ionization zone sits at the same temperature in every star where it operates, 40,000 Kelvin, because that is the temperature at which helium undergoes its second ionization, regardless of what star it is inside. But in different stars, the zone sits at different depths. In a large luminous Cepheid, the zone is relatively close to the surface. The layers above it are massive and take longer to rise and fall. In a smaller RR Lyrae star, the zone is also near the surface in absolute terms, but the star is much smaller and the oscillation completes in hours rather than days. The Kappa mechanism is one engine running inside many different machines, each machine built to a different scale, each producing a different period, but all of them governed by the same underlying physics, the same invisible valve opening and closing in the dark beneath the surface. What this means, resting with it for a moment, is that a Cephid star pulsating in the night sky is not doing something analogous to breathing, not merely resembling a rhythm. It is driven by a genuine physical cycle, a feedback loop between compression and opacity and radiation pressure, as mechanically real as the cycle inside a heat engine. The motion of the outer layers is not decorative. It is the visible surface of something happening deep inside, in a zone that no instrument has ever seen directly, and that we know about only because the star's outer layers move in ways that physics can predict and measure. The expansion and contraction of the star's radius, measurable by the Doppler shift of its spectral lines, which spread apart as the surface rushes toward the observer and compress as it retreats, traces the activity of that invisible layer with a precision that grows more remarkable the more carefully it is considered. A yellow supergiant pulsating with a period of 10 days expands and contracts by a significant fraction of its own radius with each cycle. The radius of such a star is already enormous, larger than the orbit of Mercury around the Sun, in some cases approaching the orbit of Venus, and the outer layers move through a distance that, in absolute terms, is a substantial fraction of the distance from the Earth to the Moon, completing the full inward and outward journey in about 10 days. The surface moves, it rises, it falls. The star is not a fixed, still thing in the sky. It is a body in slow, steady, mechanical motion, its rhythm set by the temperature of a hidden zone of ionizing gas, driven by the inexhaustible outward flow of energy from a nuclear core. The light curve records this motion as brightness. Near the phase of maximum compression, just before the outer layers spring back outward, the surface temperature is at its highest, and the star is also smallest. But because the rise in temperature outpaces the decrease in surface area, the star is at or near its brightest, just past this point, as the layers begin to move outward while still running hot. It is a slight offset. The peak brightness does not line up exactly with the moment of maximum compression. The exact placement of the light curve's peak relative to the pulsation phase carries information about the physics of the driving zone, and that information can be read by anyone with the patience to measure carefully. Each data point in the light curve is a single observation, a magnitude recorded on a specific night. Each observation, on its own, means nothing in particular. Strung together across one period, then 2, then 100, the points describe a shape that reveals the mechanism within. Some of the best early measurements of Cephid light curves were made not by professional observatories, but by individual observers working alone with modest equipment, recording brightness estimates by comparing the variable to nearby stars of known and stable magnitude. The work was slow and required consistency over months and years. A single gap in the record, a season of cloud, a change in instruments, a period of illness could complicate the analysis significantly. The observers who produced the best long-term records of Cephid variability were people of considerable patience, drawn to something in the work itself, rather than to any particular result it might produce. The act of watching a star night after night recording a number, returning the next clear night to record another, has a quality of sustained attention that is relatively rare in ordinary life, and that the sky seems, over time, to reward with a growing intimacy with what is being watched. Delta Scuti stars have a different quality to them when observed over many nights. The curve never repeats exactly. The multiple pulsation modes beat against each other, and the combined signal they produce passes through configurations it may not revisit for years. An observer watching such a star and recording its brightness over a week would see what looks like irregularity, rises and falls that do not quite repeat, maxima of different heights, minima arriving at slightly unpredictable times. Only with the full data set in hand and the mathematical tools to decompose it does the underlying order reveal itself. Not one frequency, but several, each perfectly regular on its own, their interference producing the apparent complexity at the surface. The RR Lyrae, stars in their globular clusters pulse with a different regularity from Cepheids, shorter, more uniform, less dramatic in amplitude. A typical RR Lyrae star brightens by half a magnitude to a full magnitude over the course of its cycle. In practice, this means becoming perhaps 2.5 times brighter at peak than at minimum, visible to the eye as a real change, but not as dramatic as the range that some Cepheids traverse. Their light curves have a shape that is somewhat less ametric than a Cepheid's, the rise a little less steep, the fall a little less gradual, the overall form approaching something more symmetric, though never quite reaching it. The shape of the curve is characteristic enough that an RR Lyrae star, once recognized, is difficult to mistake for any other kind of variable. Among some RR Lyrae stars, the pulsation amplitude changes over time in a slow multi-day modulation that cycles through periods of larger and smaller brightness variation. This is called the Blaschko effect, after the astronomer who first described it in the early years of the 20th century. Its cause is still not fully established. The leading picture involves interactions between different pulsation modes inside the star, the dominant mode and a near-resonant secondary mode influencing each other in ways that slowly modulate the total signal seen from outside. The Blaschko effect is a reminder that even in the stars considered the most regular pulsators, the underlying physics is not simple, and long patient records reveal subtleties that short observations cannot show. A night sky observer in the northern hemisphere, lying back in a dark field and watching the region around the constellation of the Lyre, cannot detect the variability of the RR Lyrae star that gave the class its name. It is too faint for the naked eye. But in the same general region of sky, a patient naked eye observer can find the bright star Eta Aquilae, one of the brighter Cepheids in the sky, and over the course of weeks, notice that it changes. It does not change dramatically from one evening to the next. The change accumulates over several days, and the observer who returns to the same sky, night after night, with some reference to nearby stable stars, will eventually perceive it. This star is not always the same. On some nights, it stands slightly above its neighbors in brightness. On others, it sits slightly below. The cycle is roughly 7 days, and the total range of variation, though modest, less than a full magnitude, is enough to be perceived once the attention is turned to it. That act of turning attention to a single star and staying with it over weeks is the entry point to all of this. The quiet, patient, repeated observation that first revealed to human eyes that the sky is not still, that individual stars change, that some of them change in ways that are regular enough to measure and predict and eventually to understand. The mechanism driving that particular star, the second helium ionization zone, the Kappa cycle, The self-sustaining thermodynamic valve is invisible. It operates in darkness, under pressure no instrument has reached, at temperatures too high for anything except radiation to survive. What is visible is only the surface motion it produces, the slow expansion and contraction, the corresponding rise and fall in brightness. The light curve is the face of the mechanism. Everything known about what lies beneath was inferred from that face, from the shape of the curve, the timing of the peak, the exact period, the Doppler shift of the spectral lines as the surface rose and fell. This inferring from surface to interior is not a workaround or a limitation. It is simply how the science works. The star shows what it shows, and from what it shows, patient analysis draws deeper and deeper conclusions about what must be happening within. The picture of the kappa mechanism, the specific temperature of the driving zone, the physics of helium ionization, the relationship between opacity and compression, was assembled over decades from exactly this kind of observation, accumulated by many people across many years, the data refined and the model tested, and the explanation gradually made more precise. No single observation was sufficient. No single night of watching resolved the question. The understanding grew the way the star's own cycle completes, slowly, through the accumulation of many small increments, each one insufficient alone, and each one necessary. The helium ionization zone sits in its fixed temperature in the dark interior of the star, absorbing and releasing. Compression comes, and the zone holds the energy. The pressure builds beneath it, patient and immense, and the outer layers begin to rise. They cool as they climb. The temperature in the zone drops below the threshold of the second ionization. The opacity falls. The stored energy pours through, and the layers, now unsupported, fall back under the weight of what the star is. They compress once more. The zone warms. The helium loses its electron again. The opacity climbs. The cycle is sealed, and it begins once more from the beginning. The star breathes. It has been breathing this way for a significant fraction of its life in this particular phase, and it will continue. The same cycle, the same period, the same invisible valve opening and closing in the same interior darkness, for as long as the conditions inside the star hold the driving zone at the right temperature and the right depth. When the star evolves further, swelling larger or contracting inward, the zone will move to a depth where it no longer drives efficiently, and the pulsation will slow and fade as the star moves on through its life. But for now, the cycle holds. The layers rise and fall. The light curve traces its asymmetric wave across the graph, and somewhere in the dark interior of the star, at 40,000 Kelvin, in a shell of helium that no eye has ever reached and no instrument has ever entered, the engine that drives it all continues its slow, self-sustaining work, absorbing, releasing, holding, letting go, holding again, when a rhythm that has been turning for millions of years, without rest, without witness, without needing either. In the middle of autumn, in a dark sky far from any town, a star appears where no star was visible the week before. It is not bright yet. It sits near the boundary between what the eye can hold and what slips away when looked at directly. That faint, uncertain zone where a point of light seems to vanish when watched and return when the gaze moves slightly aside. But it is there. Over the following nights it grows. Not quickly, not in any way that would be obvious from one evening to the next. But across a week, across 2 weeks, the change becomes undeniable. A star where the chart shows nothing of significance, and growing still, climbing through the slow ranks of brightness towards something that will eventually need no patience or dark sky or practiced eye to find. That star is Omicron Ceti. It sits in the dim constellation of the Whale, unremarkable for most of the year, invisible to the naked eye for months at a time. Then it returns. It has been returning for as long as anyone has kept records of it, on a cycle that runs close to 11 months, brightening from near invisibility to a point where, at its most luminous, it shines clearly enough to be one of the more prominent stars in its part of the sky, before fading once more over the following months into a faint orange ghost, and eventually into nothing at all, at least nothing the unaided eye can find. Johannes Hevelius named it Mira in 1662, a Latin word meaning wonderful, and the name has stayed because what it does is genuinely hard to take in the first time it is witnessed. The full range of Mira's brightness change across one complete cycle represents a difference in actual light output of roughly 1,500 times, 1,500 times more light at maximum than at minimum. That number is difficult to hold as an abstraction, so the body of the star itself is a better place to begin. At its heart, Mira is not a young star. It long ago exhausted the hydrogen in its core that had powered it through most of its life. The quiet, steady fusion that had held it stable for billions of years, the deep, continuous process that keeps a star like the Sun from collapsing under its own weight, has long since ceased to operate there. What remains at its center is a dense, inert core made almost entirely of carbon and oxygen, compressed into a volume far smaller than the star's outer appearance would suggest. Around that core, two separate shells of nuclear burning continue, one burning hydrogen, one burning helium, each igniting and fading in a slow, alternating rhythm driven by conditions in the layers around them. And beyond those burning shells, outward through an enormous extent of slowly convecting gas, lies an outer envelope so vastly extended, so cool and tenuous at its edges, that the star's radius is somewhere between 200 and 400 times the radius of the Sun, depending on the phase of its cycle. Were Mira placed at the center of the solar system, its outer boundary on some days would reach past the orbit of Mars. What such a star looks like when seen directly is not what one might expect. Through a large modern telescope, sensitive to the infrared lights that Mira emits most abundantly, it appears as a ruddy, asymmetric disk, not the clean round sphere that diagrams of stars tend to suggest, but a slightly irregular form, uneven at the edges, with bright regions and darker ones scattered across its face. Its outer atmosphere blurs gradually into the surrounding darkness rather than ending at a sharp boundary. There is no clean surface to speak of. The gas simply becomes less and less dense with distance from the center, thinning into a surrounding envelope of material that the star has been slowly exhaling for thousands of years until it fades into the background of space. The boundary between Mira and the space around it is not a line, but a long, slow dissolution. This is a star in the asymptotic giant branch phase of stellar evolution, a late chapter in the life of a star, not very different in original mass from the Sun. The phrase names the track such stars follow on the diagram that relates stellar brightness to temperature, a track that curves upward and to the right as the star expands and cools and grows luminous beyond what its main sequence life would have suggested. On this branch, the slow drama of alternating shell burning plays out over thousands and tens of thousands of years, punctuated by events called thermal pulses, brief, intense episodes in which the helium shell ignites explosively for a short time, driving convection deep into the star's interior and dredging material upward from the nuclear burning region into the outer envelope. Carbon comes up. Heavy elements forged slowly in the burning shells by the steady capture of neutrons, come up as well. The star's atmosphere gradually changes its chemical composition as this dredging continues over many pulses, and the material brought up eventually finds its way into the slow wind streaming away from the star's surface, seeding the surrounding space with elements that were not there before. Mira has been losing mass for a long time. The rate is slow by any everyday measure, perhaps 1/10 millionth of a solar mass per year, perhaps somewhat more, but stars are large and time is long, and over the course of the asymptotic giant branch phase, the total mass loss is substantial. Some fraction of the star's outer material departs in this slow wind. The pulsations of the star play a direct role in driving this outflow. Each expansion of the outer layers lifts material higher than it would otherwise reach, into the cool outer regions of the atmosphere, where the temperature falls low enough for dust grains to condense. Once dust forms, the pressure of the star's own light acts on those grains, radiation striking them and pushing and accelerates them outward, away from the star, carrying the surrounding gas with them. The pulsation is not incidental to this mass loss. The pulsation is part of what makes the loss possible. Far from Mira's visible disk, surrounding it at a distance of many billions of kilometers, this lost material forms an extended circumstellar envelope, a faint, roughly spherical shell of gas and dust that in infrared imagery appears as a glow surrounding the brighter core of the star. It is ancient material in the sense that the outermost layers of it departed the star centuries ago, and the innermost layers are more recent, and somewhere in between the material carries a record of the star's mass loss history, the way a tree's rings carry a record of its growing seasons. Mira itself, at optical wavelengths, can barely be seen through this surrounding shroud during parts of its cycle. The dust its own winds have made absorbing and scattering the visible light, making the star dimmer than it would otherwise be. Some of the variation in Mira's brightness comes from this dust, the geometry of how much has condensed and where it sits in relation to the line of sight, layered on top of the variation driven by the pulsation itself. The pulsation period for Mira runs close to 332 days, though this figure is an average. Individual cycles vary. Some maxima are brighter than others. Some minima are fainter. The spacing between successive peaks is not perfectly regular, but drifts slightly from one cycle to the next, and averaged over many decades, the period itself has shown a slow secular change, a gradual shift, amounting to a small number of days per century, that reflects changes happening deep in the star's interior as it slowly evolves along its branch. A light curve of Omicron Ceti, drawn from more than a century of careful observations, shows this drift plainly. A long, slow wave with roughly consistent shape, the peaks appearing at intervals close to, but not precisely, 332 days, the amplitudes varying modestly from one cycle to the next, the whole record spreading across more than 100 separate oscillations. Each of those oscillations took nearly a year of real time. The full record spans more than a human lifetime. It is one of the most complete pictures available of a single star's slow inner life. What drives this pulsation is a cycle operating in specific layers of the stellar envelope, a region where helium undergoes a change in its ionization state, where the opacity of the gas to radiation behaves differently under compression than it does in a simpler situation, storing energy as the layers are squeezed together and releasing it as they spring back out. The cycle has its own internal logic, and once established, it sustains itself, compress the zone, trap the radiation, build pressure, drive expansion, cool the expanding gas until the helium recombines, and then begin the inward fall again. The pulsation continues as long as the zone exists in the right temperature range, and the star moves on the asymptotic giant branch slowly enough that the zone persists there for a very long time. There is something almost tidal about it, an oscillation with a period set by the physical dimensions of the star itself, by how long it takes a pressure wave to travel from the surface down to the driving layer and return, a period that lengthens as the star grows larger and its outer layers grow less tightly bound to the core below. Mira variables as a class are defined by their large amplitudes and long periods, but those two quantities are not independent of each other. More luminous Miras pulsate more slowly, on the whole. A brighter star on the asymptotic giant branch is generally also a larger star, and a larger star has a longer period, and the relationship between period and luminosity in Mira variables is one of the ways these stars can be used as signposts of distance in the nearby universe. This is not the only thing they offer astronomers, and not the most important thing about them in the present context. What matters here is the physical truth underlying the relationship, that a star's size and its pulsation period are deeply connected, the period growing as the star grows, the two quantities coupled, the way the length of a pendulum and its swing time are coupled, one a direct consequence of the other. The range of periods seen among Mira variables runs from roughly 100 days to over 1,000, with the most extreme examples, the longest periods, found among the most luminous, most evolved stars, those deepest into the asymptotic giant branch phase and closest to the end of that phase. A period of several hundred days means that a single complete cycle, from one brightness maximum to the next, takes most of a year to run through. Watching a Mira variable is not a single night activity. Wait, it is a months-long practice, the kind of observation that generations of careful amateurs have carried out by comparing the same star, night by night, to nearby reference stars of known brightness, plotting the result and waiting for the curve to emerge from the scattered points over the following months. The curve is always there. It takes time to see. Beyond the Miras, the longer period end of the variable star world grows less orderly. Stars that pulsate in ways broadly similar to Mira variables, but with less consistency, periods that vary more noticeably from cycle to cycle, amplitudes that shift unpredictably, light curves that never quite settle into the reliable wave shape of a classical Mira, are grouped under the label of semi-regular variables. The classification divides further into subgroups depending on the nature of the irregularity. Some semi-regulars are cool supergiants, far more massive than Mira, whose variability arises from pulsations combined with other instabilities in their vast outer envelopes. Others are evolved stars similar to Miras, but at an earlier stage of development, with less well-established pulsation modes, their dominant rhythm not yet fully in control of the cycle. Still others have light curves that suggest two or more pulsation periods running simultaneously. The resulting brightness changes, a superposition of those periods, the combined wave complex, and slightly different from one cycle to the next, as the two rhythms drift slowly in and out of phase with each other. At the far end of the ordering, beyond the semi-regulars, lie the irregular variables, stars classified simply as irregular because no period can be extracted from their brightness record at all. Their light curves show slow wandering changes, brightness rising and falling over months without any repeating pattern, the variations real and measurable but not amenable to prediction. These stars are not behaving randomly in any deep physical sense, and their interiors are subject to the same physical laws as every other star, but they may be stars in which several different pulsation modes are operating with comparable strength, none dominating, the interference among them producing variations that are genuinely complex rather than simply noisy, the underlying rhythms present but entangled past the point of easy disentanglement. Or they may be stars in which the dominant mode is changing, one period waning as another gradually strengthens, caught in a transition that makes them look irregular to an observer working on a timescale of years or decades. The irregularity may be temporary. The slow changes in a star's interior structure as it moves along its evolutionary track can shift the conditions in the driving layer and alter the preferred pulsation period over centuries, and a star in the middle of such a shift might look genuinely irregular for a very long human lifetime and then slowly resolve into something more regular again. All of these stars, the Miras, the semi-regulars, the irregulars, share the common condition of being highly evolved, cool, and enormously extended. They are stars in the late chapters of their lives. Their interiors carry the record of billions of years of nuclear processing. Their surfaces are cool enough, temperatures measured only in a few thousand degrees rather than tens of thousands, for molecules to form in their outer atmospheres, for the carbon and oxygen dragged up from the burning shells to combine into carbon monoxide, for titanium oxide to form and absorb light in characteristic patterns that appear in their spectra as dark bands rather than the smooth curves a hotter star would produce. The spectra of Mira variables are complex and change with the phase of the pulsation cycle, the atmospheric layers shifting in temperature and density as the star expands and contracts, the molecules forming and dissociating in step with the rhythm, the spectrum itself a moving picture of what the outer atmosphere is doing at each moment in the oscillation. The light a Mira sheds on the world is almost entirely infrared. At the wavelengths the human eye is tuned to, a Mira near minimum is a faint orange smudge if it can be seen at all. At infrared wavelengths it blazes, a powerful emitter dumping vast amounts of energy into the longer wavelengths that cooler surfaces radiate most efficiently. The brightness change across a Mira cycle is less dramatic in the infrared than in the visible. The amplitude narrows because the star's temperature changes as well as its size, and the visible light is more sensitive to temperature than the infrared is. At maximum, the outer atmosphere is fractionally warmer than at minimum, and that extra warmth pushes more of the emission into visible wavelengths, amplifying the visible brightness change beyond what the total luminosity change alone would produce. The full range from magnitude 2 to magnitude 10, which the eye of an observer watching Mira over its cycle might experience, would correspond to a star crossing from one of the more prominent points in an autumn sky to one too faint to find without optical aid. Some Mira variables have been watched for more than 3 centuries. The very first recorded observation of Omicron Ceti's variability came in 1596, when David Fabricius, a Dutch astronomer, noted a star in the Whale that he had not seen before, catalogued it, and found later that it had faded. He saw it again in 1609 and realized it had reappeared. The period was not established from those early observations alone. The data were too sparse, too irregularly spaced, but they anchored the beginning of a record that has grown more detailed with every subsequent generation of observers, each adding their measurements to the accumulating light curve, the curve growing longer and richer across centuries. Today, the light curve of Omicron Ceti is one of the longest continuous brightness records of any astronomical object maintained by observation, a line drawn across time from the early 17th century to the present, each point placed there by a specific person on a specific night. The line itself, a kind of collaboration stretched across 400 years. Watching that curve laid out across its full length, a few things become visible that are not apparent in any single cycle. The average period has drifted. The amplitude varies from maximum to maximum, sometimes reaching higher, sometimes stopping short. There are anomalies, places in the record where the expected maximum did not come as bright as usual, or where the decline from maximum paused for a brief time before resuming, or where two observers working simultaneously measured slightly different values because they were comparing the star to slightly different reference stars and needed careful calibration to bring their observations into agreement. The long record contains the imperfections of real observation as well as the signal of the star itself, and separating the two is part of the careful work of those who study it. But the signal is there, the wave is unmistakable, and what it represents, reduced to its essence, is a star the size of the inner solar system, breathing in and out on a rhythm close to 11 months, losing a little of itself each cycle into the surrounding space, carrying in its slow exhalation the elements it made in its core across billions of years of life. There is a kind of time embedded in this that is not easy to hold, but is worth approaching slowly. Mira has been pulsating on this same rough rhythm with this same rough amplitude for longer than there have been human beings on Earth. The cooling that would eventually end the sun's main sequence life is still billions of years away, but Mira already passed that point in its own history so long ago that the star it was then has no living record anywhere. The carbon now drifting outward in its slow wind has been inside a star since before the formation of the solar system. It was made in nuclear burning shells operating under conditions no laboratory can produce. It will drift outward into the surrounding cloud, cool, and eventually, over spans of time that make the history of human observation look very brief, join the raw material of future stars and planets and possibly other forms of complexity entirely. The circumstellar envelope surrounding Mira, as seen in deep infrared exposures, is not a simple sphere. It is irregular, its boundary uneven, with denser regions where mass loss was higher during particular epochs and thinner regions where it paused or diminished. Embedded in its structure is a record of the star's mass loss history over thousands of years, the accumulated output of all the pulsation cycles that preceded the ones astronomers are watching now. Some of the material in the outer reaches of that envelope departed the star when the Roman Empire was still a living institution. Some of it departed before recorded history began. The envelope is, in a quiet way, one of the oldest human timescale objects in the sky, older in its outermost layers than any artifact, any building, any written language, and it is still growing, still being fed by the slow continuous outflow from the star at its center. Semi-regular variables, when observed over long enough periods, often reveal structure in their apparent randomness. A star classified as semi-regular because its period varies noticeably from cycle to cycle may, when examined across a span of decades rather than years, show a slow modulation of its average period, a gradual lengthening or shortening of the typical time between maxima that suggests the star is slowly evolving, its size changing on time scales that are long relative to any individual cycle, but short relative to the star's age. Some semi-regulars have been observed to make transitions. A star that was irregular or semi-regular over a recorded span of years begins in later observations to show more consistent period behavior, as though a dominant pulsation mode has gradually established itself over the noise of competing oscillations. Others go the other direction, a previously regular period becoming less reliable as the star evolves into a region of the asymptotic giant branch, where the conditions driving the dominant mode become less well defined. The cool supergiants among the semi-regulars, stars many times the mass of the Sun, luminous enough to be visible across great distances, add their own character to this class. These are not stars destined to shed their envelopes gently and settle into white dwarfs the way Mira will eventually do. They are stars that will end in core collapse, in the violent rebalancing that occurs when a massive core can no longer support itself and the outer layers fall inward and then explode outward. But in the long period before that end, they sit in the sky as cool, red, slowly brightening and dimming points, their variability not announcing what is coming, but simply recording the present condition of their vast, slowly convecting outer envelopes, where the balance between gravity and the pressure of hot gas from below is maintained across a volume so large that convective cells, the slow overturning currents that carry heat from inside to outside, can be individually larger than the entire Sun. Betelgeuse, in the shoulder of Orion, is perhaps the most familiar of these, a semi-regular variable bright enough to be one of the more conspicuous stars in the winter sky, its orange color and modest brightness variations visible to the careful naked eye over months. Its light curve over the past century shows a rough period of a few hundred days embedded in a larger and slower brightness modulation, running over roughly 6 years, the two cycles overlapping to produce variations that are real but not fully predictable from any simple formula. In 2019 and into early 2020, Betelgeuse faded noticeably from its usual brightness, dimming to a level that attracted wide attention before recovering over the following months. The explanation settled on involved a massive cooler gas ejected from the stellar surface, blocking some of the outgoing light before dissipating into the surrounding space. The event was unusual in degree, but not in kind. A star of that size at that stage of its life ejects material from its surface continuously. A particularly large ejection simply produced a dimming that was unusually clear to observers watching from a planet 800 light-years away. All of this, the Miras and semi-regulars and long-period irregulars, the mass-losing evolved giants, and the pulsating asymptotic giant branch stars, belongs to a category of stellar life that is in some ways more alive to the senses than the quiet, stable middle age of a star like the Sun. The Sun will undergo a version of this eventually. In about 5 billion years, its hydrogen core exhausted, it will begin to expand and cool, ascending the red giant branch and then the asymptotic giant branch, developing the alternating burning shells and the thermally pulsing layers and the slow convective dredge-ups that will transform its composition and drive a slow wind of material into the surrounding space. It will lose perhaps half its total mass in that phase, its outer envelope dispersing over tens of thousands of years into an expanding shell of gas and dust that for a brief cosmological moment will glow as a planetary nebula, the illuminated remnant of a stellar wind, a last slow exhalation made briefly visible by ultraviolet light from the cooling core left behind. The Sun will pass through something like what Mira is doing now, at some future time so remote from the present that no human measure reaches it. For the moment, Mira continues on its 11-month rhythm, indifferent to the fact of being watched, growing slowly brighter through autumn and into winter, the change happening on a time scale that fits within a season, within a year, within a human span of attention. Each maximum it reaches is slightly different from the last. The period drifts. The star itself is changing, very slowly, across the centuries of human observation. The light curve drawn from all those observation nights each point placed there by a person standing in the dark, comparing a faint orange star to its neighbors, and writing down a number is a record of a process so large and so slow that no single lifetime can contain it, but that any single lifetime can contribute to. The dust that Mira has been losing for thousands of years drifts outward through the surrounding space at speeds measured in a few kilometers per second. Slow by the standards of stellar winds from hot, massive stars, but steady and continuing season after season, cycle after cycle. The material accumulating in the growing circumstellar envelope around a star that is in its own gradual way dispersing itself into the larger medium of the galaxy. Carbon grains the size of small molecules, silicate particles, the occasional complex molecule assembled from atoms that spent billions of years inside a star and are now cooling in the near vacuum of interstellar space, drifting in the long dark between stars with no destination and no urgency, simply present in the galaxy the way all matter is present, enduring, unhurried, carrying the record of the processes that made it in the particular ratios of its elements and the particular structure of its grains. The envelope around Mira and around every other star at this stage of its life is a dispersal. It is the star returning its accumulated material to the common store. The elements that arrived in the molecular cloud that eventually became the star, hydrogen mostly, some helium, small quantities of everything else, leave enriched. The carbon and nitrogen and oxygen built in the burning shells, the slow neutron capture elements assembled over long years of nuclear processing. All of it drifts out into the surrounding space as the star sheds its outer layers. The circumstellar envelope will eventually merge with the interstellar medium, its material diluted into the general background of the galaxy over timescales of hundreds of thousands of years, no longer identifiable as coming from any particular star, simply part of the diffuse material from which the next generation of stars and planets will eventually form. In the dark sky of a clear autumn night, the faint orange point of Mira, growing slowly brighter above the horizon as the weeks pass, carries none of this visibly. It is simply a star returning to visibility after months of absence, a star any patient observer can find if they know where to look and allow their eyes enough time to adjust. The scale of what is happening inside it and around it and ahead of it is not written in its color or its position. It is written in the long, slow curve of its brightness over time, that accumulating record drawn point by point across more than 4 centuries of careful watching, and in the faint infrared glow of its surrounding envelope expanding outward in all directions at the pace of a slow drift, carrying the star's long interior history with it into the dark and the cold and the quiet that has no end. A star appeared in the sky where no star had been the night before, not a planet drifting along its slow arc, not a satellite catching the sun at a low angle. A star, a fixed point of light in a familiar part of the sky, sitting among stars that had been there for as long as anyone had thought to look, and yet not there yesterday, and bright enough tonight to see without any instrument at all. The constellation it had joined was unchanged in every other particular. The surrounding stars held their usual distances, their usual faint or steady glows. Only this one was new, and it had not been made overnight. And it had been there all along, a white dwarf in a close binary system, too faint on its own to register against the dark until the night it was not. That is what a nova looks like from Earth. Not an explosion in any sense the eye can follow. No fireball, no expanding ring of light, visible in real time, no sound crossing the void between, just an absence, and then a presence, a point of light written into a constellation that had no room for it. What had happened in the hours or days before was this: the white dwarf, a star no larger across than the Earth, but carrying nearly the mass of the Sun compressed into that small space, had for a long time been drawing material from a companion star orbiting close beside it. Hydrogen from the companion's outer layers, pulled across the narrow gap between them, had settled slowly onto the white dwarf's surface. This was not a fast process. It was patient, accumulating grain by grain across years or decades, the layer growing thicker and denser and hotter under its own weight. Then the temperature at the base of that accumulated layer reached a threshold. The hydrogen ignited, not in any controlled or gradual way, but in a runaway cascade that spread across the entire surface in a fraction of a second, blasting the outer material away at speeds of hundreds of kilometers per second, and releasing, in those brief hours, energy enough to outshine the combined light of 100,000 ordinary stars. The system brightened by a factor of tens of thousands. It became visible across great distances, written into the night sky without warning, a new point of light where watchers found only absence the evening before. Then it faded. Over days and weeks and months, the nova's expelled shell thinned and cooled. The system settled back toward its previous faint state. The white dwarf, still there, still orbiting its companion, began to draw in fresh material, and the slow accumulation started again. This is what distinguishes a nova from a single catastrophe. The white dwarf survives, the companion survives, the orbit continues. The patient accumulation of hydrogen begins again on the surface of the surviving white dwarf, and somewhere far ahead in time, another threshold will be crossed, another runaway will ignite, and the system will briefly blaze back into visibility. For some systems, that return takes thousands of years. For others, far less. In the constellation Ophiuchus, there is a binary system called RS Ophiuchi that has done this at least 6 times within recorded observation. It erupted in 1898. It erupted again in 1933, and then in 1958, and then in 1985. Each time it briefly became bright enough to see without a telescope, held that brightness for some days or weeks, and then retreated back into the dark. It came back in 2006 and again in 2021, when observers who had been waiting for it, some of them for years, saw it climb once more into naked eye visibility in the late summer sky. The white dwarf at the center of RS Ophiuchi is thought to be very close to the upper limit of what a white dwarf can weigh before the accumulated mass triggers not just a nova eruption, but something far more complete. That limit is roughly 1.4 times the mass of the Sun. At or above it, no known force can hold the white dwarf together, and what follows is not a brightening, but a total detonation, a Type 1a supernova, the star converting its entire mass to energy in a fraction of a second. RS Ophiuchi has not yet reached that limit, but each eruption deposits a small net gain of mass onto the white dwarf, and over time the balance shifts. There is no way to know when. There is no urgency in that not knowing. Whatever happens will happen on a timescale that the word patience cannot adequately hold. For now, the system continues its slow rhythm. A cool giant fills one part of the binary's orbit, pulsing gently on its own long cycle. A white dwarf, hot and compact and silent in the way that very dense things are silent, circles it, drawing gas from the giant's extended outer atmosphere, building up again toward its next eruption. The sky above any given observer may be clear or clouded on the night it next appears. It will not wait for a clear night. Not all of the stars that flare and brighten are doing so because of borrowed fuel igniting on a white dwarf surface. Some are very young, and their variability comes from the chaos of formation itself, from the process of becoming a star not yet complete. In the dark interior of a molecular cloud, a region of space where gas and dust lie so thick that the light from the stars behind cannot pass through, a young star sits embedded in the material it has not yet cleared away. It is still contracting, still pulling gas onto its surface from the disk of material swirling around it. The gravity of its growing mass draws streams of that disk material inward along magnetic field lines, and where those streams strike the stellar surface, they hit hard, creating hot spots, bright localized patches, perhaps 1,000 degrees warmer than the surrounding photosphere, that flare and shift as the streams vary in intensity. The star's own magnetic field is tangled and active, generating dark spots across the surface that rotate in and out of view as the star spins, dimming it briefly as they face forward, brightening it slightly as they rotate behind. Material from the disk rains down in irregular pulses. The star brightens, the star dims. Sometimes there are faint jets of gas streaming outward from the poles, and sometimes those jets pulse, and the brightness record of this young and unsettled object jumps and dips on timescales that range from hours to years, with no clean period, no regular wave, just the noise of a body still finding its shape. These are called T Tauri stars, named after a prototype star in the constellation Taurus that sits inside one of the most studied star-forming clouds in the sky. A T Tauri star is not yet fusing hydrogen in its core, the way a settled main sequence star does. It is still being made. The fusion that powers it comes from gravitational contraction, from the slow falling inward of its own mass, which releases energy as heat and light, the way any falling thing releases energy when it finally stops. That process will continue for a few million years, which is brief by astronomical standards, before the core temperature and pressure reach the point where hydrogen fusion ignites fully and the star stabilizes onto the main sequence and becomes from the outside much quieter. But in the cloud, in the dark, it is anything but quiet. The T Tauri star sits surrounded by the debris of its own formation, a thick disk of gas and dust that may one day coalesce into planets, swirling slowly and feeding streams of material back onto the star at irregular intervals. The brightness record of one of these stars, plotted as a light curve over years, looks nothing like the smooth sinusoidal wave of a pulsating variable. It looks like a record of something unfinished, a jagged and unpredictable line that rises and dips without repetition, the signature of a process that has not yet settled into a pattern because no pattern has yet formed. From a distance of many light years, a Centauri star is just a faint and variable point in an otherwise dark part of the sky, slightly reddened by the dust between, and nothing in its appearance suggests the turbulent surface, the raining streams of infalling material, the hot spots glowing 1,000 degrees above the temperature of everything around them. All of that is reduced by distance to a small brightness change in a long series of photometric measurements. The science lies in reading backward from that faint brightness change to what must be happening, unseen, at the surface. Some variable stars change brightness, not over days or months or years, but in seconds, and not in the soft, regular way of a pulsating giant whose outer layers rise and fall, but in a sudden spike so abrupt that a light curve that had been perfectly flat becomes a near vertical line within the space of a single measurement. In the direction of the constellation Cetus, At a distance of less than 9 light years, there is a red dwarf star called UV Ceta, intrinsically so faint that despite its closeness, it cannot be seen without a telescope on a clear night. On most nights, it sits below the threshold of naked eye visibility, small and dim in the way that red dwarfs always are, radiating most of its light in the red and infrared, its surface temperature only a fraction of the sun's. But UV Ceti is what astronomers call a flare star, and every so often, unpredictably, without warning, it produces an event that lasts less than a minute, and yet releases in that minute more energy and ultraviolet light than the star normally produces in hours. The mechanism is magnetic. Deep in the star's interior, convection, the slow churning of hot gas rising and cool gas falling, drags and twists the star's magnetic field into complicated, stressed configurations. At the surface where this stressed field emerges, the field lines of opposite polarity can come close enough together to snap and reconnect in a sudden rearrangement, releasing the stored magnetic energy as a burst of plasma and radiation. This is magnetic reconnection, the same process that drives solar flares on the sun, but on a red dwarf with a fully convective interior and an exceptionally tangled field. The events can be proportionally far more powerful relative to the star's total output. A single flare on UV Ceti can brighten the star's ultraviolet emission by several magnitudes in the space of seconds, far too fast for most traditional observational methods to capture cleanly. A photometric record of a UV Ceti flare looks startling compared to everything else a variable star produces. There is nothing gradual about it. The light curve runs flat for hours, varying by only a tiny fraction at most, and then there is an almost instantaneous vertical rise, a spike, reaching its maximum in seconds before fading more slowly over the following minutes. The asymmetry is total. The rise and the fall are not the same shape at all. The rise is a wall, the fall is a gentle slope, and then the curve flattens again, as if nothing had interrupted it, and the star returns to being a faint, unremarkable red point in a dark field, waiting for the next reconfiguration of its tangled field to snap somewhere else at the surface. Red dwarfs are the most common type of star in the galaxy. The majority of the stars within 100 light years of the Sun are red dwarfs, nearly invisible individually, but constituting most of the stellar population by number. A large fraction of them are flare stars to some degree, especially the younger and more magnetically active ones. UV Ceti has a companion of the same type, a slightly less active red dwarf, orbiting close beside it, and the two together have been observed and catalogued and studied for long enough that their individual flaring rates are reasonably well characterized, not predictable in the sense of when the next flare will occur, but statistically, on average, approximately this often, approximately this bright. The unpredictability is honest. Magnetic reconnection events of this kind involve the behavior of plasma in a stressed field, and small differences in initial conditions can push them toward very different outcomes. A flare might last 15 seconds or 15 minutes. It might brighten by half a magnitude or by 3. The surface of the star holds no memory of which direction the energy will go when the field finally snaps, and neither do the instruments watching from a great distance. All of this, the nova's thermonuclear surface event, the T-Tauri star's chaotic infalling streams, the flare star's sudden magnetic snap, represents brightness changes driven by a single object or a single process at a single location in space. The source of the variation is physically concentrated. A nova erupts from a specific small layer on the white dwarf's surface. A flare rises from a single reconnection event at a specific site on a red dwarf's corona. the rest of the star is unchanged. But there are other variable systems in which the variability itself is spread across the entire structure of two stars bound together, in which the brightness of the system shifts because the relationship between the two components is always slowly changing. A symbiotic star is a binary system built of two objects that have almost nothing in common. One is a large, cool, evolved giant, often the kind of slowly pulsating giant that is expanded to fill a vast volume of space, its surface temperature low enough to allow molecules to form in its outer atmosphere, its color deep red or orange. The other is a white dwarf, tiny and dense and radiating at temperatures of tens of thousands of Kelvin, surrounded in many cases by a disk of accreted material and by a nebula of gas, ionized by its own intense ultraviolet output. These two objects orbit each other on periods that may range from years to centuries, and from most angles the system is a single unresolved point of light whose combined spectrum carries contradictory signatures. The cool molecular absorption bands of the giant mixed with the hot emission lines of the ionized gas surrounding the white dwarf, two entirely different temperature regimes, producing their light in the same few arc seconds of sky. The variability of a symbiotic system is not simple. It comes from several sources at once, layered one on top of another, and they operate on different timescales. The giant pulsates on its own long period, months to years, and as it brightens and dims in its usual slow way, the total light of the system rises and falls with it. The white dwarf accretes material from the giant's wind, and that accretion is not perfectly steady. The disk around the white dwarf can brighten or flicker on timescales of hours as the rate of infalling material changes. And in some symbiotic systems, the hydrogen accumulating on the white dwarf burns not in explosive nova outbursts, but in a quasi-steady thermonuclear glow, producing a soft ultraviolet and X-ray luminosity that slowly brightens and fades on its own schedule. In the optical light that most ordinary telescopes detect, all of these processes blend. The light curve of a symbiotic system over years shows variations from the giant's pulsation, shorter-term fluctuations from the accretion disk, and occasional outbursts when the burning on the white dwarf's surface intensifies. No single mechanism owns the curve. Reading a symbiotic light curve requires pulling apart these overlapping contributions, separating the giant's slow wave from the white dwarf's flicker, and the tools that do this most cleanly are not photometry alone, but spectroscopy, measuring the star's light broken into its wavelengths, which can distinguish the cool giant's spectral signature from the hot white dwarf's surrounding glow, even when the two cannot be resolved into separate points. The giant in a symbiotic system does not know it is orbiting a white dwarf. It pulsates as it would pulsate if it were alone in space. It loses mass through its slow wind, as evolved giants do, and some of that wind falls toward the white dwarf because the white dwarf is nearby, and its gravity reaches across the orbital distance. The giant does not accelerate its wind toward the white dwarf by any active means. The material simply disperses into the space between them, and the fraction of it that falls within the white dwarf's gravitational reach is captured. The rest continues outward into the surrounding space and is lost to both. This is the geometry of a wide binary, and it is very different from the geometry of a close binary, like RS Ophiuchi, where the companion is near enough to the white dwarf that a direct stream of material is drawn across the gap, from one star to the other. In the wide symbiotic orbit, the exchange is diffuse, but it is still an exchange, still an ongoing slow redistribution of mass from a dying giant into the dense remnant beside it, and it has been going on across millions of years. From far away, The system is two stars that cannot be individually distinguished. The optical light arrives mingled, carrying the mixed signatures of cool and hot, of pulsation and accretion, of slow variation and sudden flicker. Something has always changed each time the system is observed. The particular combination of what has changed and on what time scale is what characterizes it as symbiotic rather than as any simpler kind of variable. The category of eruptive and cataclysmic variables, novae, flare stars, T-Tauri stars, symbiotic systems, does not form a single family in the way that pulsating variables do. Pulsating variables share a single physical mechanism, the kappa mechanism operating in the deep ionization zones, running the same thermodynamic cycle in different stellar masses and temperatures. But eruptive and cataclysmic variables are linked only by the property that their brightness changes are driven by something outside the steady interior of a single star. Mass transfer from one body to another, magnetic fields growing stressed enough to snap, in falling material striking a young star's surface at irregular intervals. Each of these processes is in its own way a boundary condition. The star is not changing from within. Something is arriving at it from outside, or something on its surface is being rearranged by a force that reaches from outside the photosphere. The variability is not a breathing, it is a response. That distinction is worth holding for a moment in the mind because it changes what a light curve means. A smooth sinusoidal rise and fall over 100 days tells a story about the interior of the star, about the ionization state of its deep layers, about the thermal structure of the zones where radiation is trapped and released. But a sudden spike on an otherwise flat photometric record, or a sharp dip that lasts a day and then recovers, or a slow multi-month rise followed by an irregular fading, these tell stories about something external, something happening near the star or at its surface, something that involves a companion or a disk or a magnetic field that has grown complicated. The sky holds all of these stories simultaneously, each star carrying its own light curve forward through time, each brightness change encoding something different about the source. An observer who has recorded hundreds of light curves begins to recognize their shapes the way a reader recognizes the form of a sentence, not by analyzing each element, but by seeing the whole pattern and knowing from long familiarity what kind of thing makes a curve of that shape. A nova rises fast and fades slow, a flare spikes and decays, a T-Tauri star jumps and dips with no clean period. A symbiotic system shows a slow pulsation wrapped around a faster flicker. Each shape has a source. Each source has a physics. The night sky seen by the naked eye gives no sign of any of this. The stars appear fixed and constant, distributed across the dark in their old familiar patterns, each one a point with no apparent motion and no apparent change. A person who has never seen a light curve would have no reason to suspect that any of them are anything other than steady. The variability is mostly small, mostly slow, mostly invisible without instruments and long records and careful comparison, but the light curve is there. For every bright star in the sky, and for millions of fainter stars below naked eye visibility, there is or will be a record of its brightness over time, a graph whose shape encodes everything the star has been doing, while the human eye registered only a point. Some of those graphs are sinusoidal and smooth. Some are jagged and irregular. Some show a slow, gentle wave that has been repeating for longer than any civilization has recorded. Some show a sudden spike that was over before the second measurement could be made. And some show the overlapping rhythms of two stars, so unlike each other, so different in size and temperature and evolutionary stage, that their combined light arrives at any given detector as a blend of all those different timescales at once. In the weeks after the 2021 eruption of RS Ophiuchi faded, the system returned to its pre-nova faintness and became invisible to the naked eye. The cool giant at its heart returned to its slow pulsation. The white dwarf, intact and warm from the blast, began to cool at the surface, while fresh hydrogen drifted across from the giant's wind and settled onto the still hot remnant of the previous explosion. The night sky over the constellation Ophiuchus looked again as it had before the eruption, the same stars in the same arrangement, the same faint background field, unresolved by unaided vision. Nothing marked the location of RS Ophiuchi. Nothing suggested that a thermonuclear event had briefly made it visible to the whole sky. Only weeks before, the accumulation had already begun again. The hydrogen settling onto the white dwarf's surface was too thin to measure, too new to detect, far from the layer thickness that would eventually trigger the next runaway. Between the last eruption and the next, many years would pass, possibly a decade, possibly more. The system would remain invisible to casual observation throughout. The pair of stars would continue their slow orbit around their common center, the giant pulsating on its months-long cycle, the white dwarf quietly gathering material from the wind, the accretion disk glowing faintly in ultraviolet light that no unaided eye would ever see from the ground. A flare star in the constellation Cetus was quiet on that same night. Its magnetic field, always tangled, had not yet found the stressed configuration that would snap. The photometric records from telescopes that had been watching it for years showed its usual low-level variation, tiny fluctuations in brightness as active regions on its surface rotated in and out of view, none of them large enough to alter the star's total output by more than a fraction of a percent. It would flare again. It always did. But not tonight. Not at the moment any particular instrument happened to be collecting its light. Somewhere in the nearest star-forming cloud, the young T-Tauri stars continued their slow contraction. The disks around them turned on timescales of days and years, feeding streams of material onto surfaces, still gathering mass, still building toward the hydrogen fusion that would eventually stabilize them. The light curves of those young stars, plotted over years, were long and jagged, and full of the ordinary noise of formation, the hot spots rotating, the disk streams varying, the magnetic field at the surface generating spots and flares and irregular jets. None of it looked like the smooth, regular pulse of something already settled. All of it was the record of something in the process of becoming. And among all the faint, unresolved points in the old familiar sky, the symbiotic systems drifted on their long orbits. The cool giants at the heart of each system pulsated on their own slow timescales, brightening and dimming over months, unaware of the small, dense, hot companions beside them. The white dwarfs gathered material from the giants' winds, their accretion disks flickering with the irregularities of infalling gas, their surfaces glowing with the quiet warmth of quasi-steady hydrogen burning. The optical light from each system arrived at Earth mixed and layered, carrying the simultaneous signatures of several different physical processes running on several different timescales, the cool and the hot, the slow and the fast, blended into a single faint point that a patient observer with a long enough record could, with effort, begin to read. All of it, the nova and the flare and the infalling stream and the slow symbiotic orbit, was variation. All of it was change in the brightness of a star, measured in the same units of magnitudes against time, plotted as a point on a graph by an instrument somewhere on the surface of the Earth or in orbit above it. The physics behind each kind of change was entirely different. The origins were different, The timescales were different, the stellar populations were different, but the raw phenomenon was the same in each case, a star that was not exactly the same brightness each time the instruments returned to it. The sky continues this way, always. New novae will appear and fade before the next ones. Somewhere at this moment, a red dwarf's magnetic field is stressed enough that in the next hour, or the next week, or the next month, it will snap and send a flare spike across the nearest photometric detector. Young stars and forming clouds are brightening and dimming on their own chaotic schedules, each one carrying a light curve so irregular it barely looks like a light curve at all. And the slow, close binary systems, the symbiotic pairs, the novae in waiting, continue their orbital rounds, accumulating mass in small patient increments, their light curves carrying the mixed signatures of everything they contain. None of them announces itself. No new point of light holds steady in the familiar sky on any particular night to flag that something is happening. The changes are mostly slow, mostly small, mostly invisible, without instruments and records and time. The sky looks the same tonight as it looked last night, to any eye not equipped to measure it, but the records exist. Somewhere in archives built from decades of photometric survey data, the light curves are there, 100 years of Mira's brightness plotted point by point, the irregular jumping of a Tauri star in Taurus, the sudden spike of a UV SETI flare recovered from old photometric records and plotted for the first time years after the event, R.S. Ophiuchi's 6 eruption history drawn across a century of professional and amateur observation alike. And in among the photometric records of the symbiotic systems, the slow double signature of a cool giant and a hot white dwarf drifting around each other over years, their combined light encoded in a long layered, multi-threaded curve that rewards patient reading with a picture of 2 entirely different stars, carrying 2 entirely different histories and temperatures, and yet arriving at every telescope as a single quiet, slowly shifting point. 2 stars, too far apart to resolve, too different in nature to describe with a single word. Circling each other on an orbit measured in years, the giant pulsating on its own long rhythm, the white dwarf flickering on its much shorter one, the 2 of them bound together by gravity into something that looks, from this distance, like one thing. The light arrives mingled. It has been traveling for a long time through empty space, and by the time it reaches any instrument, its origins are mixed together and cannot be separated by the eye alone. Only the slow accumulation of measurements, taken over many nights and many years, makes it possible to hold the 2 components apart in the mind simultaneously, to see the giant and the white dwarf as separate objects, each with its own life and its own time scale, sharing only their orbit and the long, slow patience of their common sky. In the constellation of Perseus, on any clear autumn night, there is a star that dims and brightens with the patience of something breathing. It does not announce this. It sits in the same position it has always occupied, between the bright anchor of Mirfak and the fainter chain of stars that loops toward the Pleiades, and from one night to the next it looks almost the same. Almost. A careful observer, someone who has spent many evenings watching, who has learned to hold a comparison star lightly in the peripheral field and judge the brightness of Algol against it with quiet, unhurried attention, that observer would notice, across the span of 3 nights, a change. The star has fallen. Where it once matched its neighbor easily, now it sits a full step fainter, reduced, as though something has come between the star and the watching eye. Something has. This is where the shape of variability turns from inward to outward. Not every star that changes does so from within. Some change because the universe, from where the watcher stands, arranges itself into a particular geometry, two stars in a single system, orbiting a common point, their plane tilted so that one periodically crosses the face of the other and blocks a portion of its light. The star has not changed. The star has merely been, for a time, partially covered, and what the observer sees, recorded night after night in small, careful marks on a chart, is a dip in the light curve that returns on a clock as reliable as any tide. The dip in Algol's brightness lasts about 10 hours. Every 2 days and 21 hours, the fainter, cooler, larger star, the one that is, in apparent terms, the dimmer component, moves across the face of its hot, bright companion, and the total light arriving from the system falls by about a full magnitude. To the careful naked eye, this is perceptible. To a photometer, it is precise and repeatable, and in that repetition, in the exact return of the same dimming on the same schedule, the geometry of the system is encoded as clearly as if the orbit had been drawn in ink. John Goodricke measured this dip in 1782. He was 18 years old. He had been deaf since early childhood, and he worked with a patience and a systematic attention that the observation of faint stars requires in unusual measure. Over many evenings at the window of his family's house in York, he timed the brightness changes of Algol carefully enough to determine not only the period, but the correct explanation, that the light was being periodically blocked, not physically changing. He did not live long enough to see his hypothesis confirmed. He died at 21, from what was likely the cold of those long watching nights. The data he left behind was correct. What Goodricke observed in that dip is now understood in full detail. The Algol system contains 3 stars, but 2 of them form the close pair that produces the regular eclipse. The brighter star, the one whose face is periodically covered, is a hot blue-white star, roughly 3 times the mass of the Sun. The star that covers it is larger in physical size, cool, orange, and much less massive. This arrangement seemed for a long time paradoxical. The less massive star had evolved faster, becoming a giant, and the more massive star remained young and bright on the main sequence. This seemed to violate what was understood about stellar evolution, in which the more massive a star is, the faster it burns through its fuel, and the sooner it expands. The resolution arrived slowly. The giant had not always been the less massive star. It had once been heavier, the dominant member of the pair, and it had evolved first, expanding as giants do, until its outer layers drifted close enough to its companion to be caught by the companion's gravity. Over long periods, material had flowed from the larger star to the smaller one, reversing their mass ratio, leaving the original giant stripped of much of its substance, and the original secondary, now heavier and hotter and wearing the accumulated mass of its partner. The system we see tonight is the end state of a long, slow transfer, a quiet exchange conducted across millions of years between 2 bodies, too small from here to separate with the naked eye. The light curve still carries all of this. Oscillations in the shape of the dip, not perfectly flat at its minimum, not perfectly sharp at its edges, in the slight color change as first one limb of the giant crosses the bright face, and then the other, in the secondary minimum, 12 hours later, when the giant is partially hidden behind its companion. None of this is visible directly. All of it can be read in lamplight, from a graph. A beta Lyrae system carries a different kind of record. In Algol, the 2 stars are far enough apart that between eclipses the light curve sits essentially flat. The brightness is what it normally is. The dip is a punctuation mark in an otherwise level line. But in a system like beta Lyrae, The two components are so close to each other and so distorted by each other's gravity that the light never reaches a flat resting point at all. It rises from one minimum, passes through a small maximum, falls into a second minimum, rises again through another small maximum, and repeats, a continuous, smooth oscillation that runs through every phase of the orbit without settling anywhere. The stars in Beta Lyrae are not spherical. They cannot be. Gravity from a near neighbor, strong enough at that distance to reshape the surface of a star, pulls each component toward the other, elongating both into forms that are wider along the axis connecting them than across any perpendicular. From the observer's vantage point, the two stars present a constantly changing projected area. When they are end-on, when the long axes of both elongated bodies point toward the observer, less surface area is visible and the system is fainter. When they have rotated a quarter turn and the broadest faces are presented, the system is brighter. No eclipse is required. The geometry of a tilted stretched pair in orbit produces the variation without either star ever blocking the other. The companion in Beta Lyrae, the one that receives material streaming from the more evolved primary, is embedded in a thick disk of gas so optically dense that the star itself cannot be seen directly. The disk was known to exist from the way the spectrum behaved, from the way the light varied, from the asymmetry in the light curve's two maxima, one slightly brighter than the other, suggesting that the hottest region in the disk faces the observer at one phase and faces away at another. That the companion was truly hidden inside the disk was confirmed only in 2008 through a technique that combined the light from multiple telescopes separated by hundreds of meters, resolving detail far beyond what any single mirror could achieve. What emerged from that analysis was an image of the system. Two elongated bodies, the disk surrounding one, the whole structure fitting into a space smaller than the distance from the Sun to Mercury. The Beta Lyrae type takes its name from this one system, this one close and distorted pair. There are many others, close binaries, whose components fill or overflow the surfaces, called Roche lobes, the teardrop-shaped gravitational boundaries within which material remains bound to one star rather than the other. When a star fills its Roche lobe, its surface reaches the gravitational balance point between the two bodies, and material at that point is free to flow. The light curves of all these systems share the continuous undulation, the absence of any flat portion, the smooth double humps that repeat each orbit. The shape of the curve is the shape of the geometry. On a cooler star, in a quieter system, a different kind of surface variation produces a different kind of light curve. The BY Draconis variables are named for a dim red dwarf in the constellation Draco, a star less than half the mass of the Sun, orange-red and faint, invisible to the naked eye. It was found to vary, not because it is eclipsed by a companion, and not because it pulsates, but because its surface is not uniform. It carries large dark regions, star spots that are cooler than the surrounding photosphere, and as the star rotates, those dark regions move across the visible face, reducing the total light reaching the observer when a large spot group is near the center of the disk. The mechanism is the same as the mechanism that produces sunspots, but on a larger and more active scale. The Sun rotates slowly, once in roughly 27 days, as seen from Earth, and its spots, while numerous in active periods, cover only a small fraction of the total surface. A Bidraconis star rotates faster. Many of these small, magnetically active dwarfs have been spun up by tidal interaction with a close companion, or simply retain the rapid rotation of their youth because they have not yet shed it to their stellar winds. That faster rotation drives a stronger internal magnetic dynamo, and that stronger dynamo raises spots that can cover a substantial part of the visible hemisphere. In the false color images produced by a technique called Doppler imaging, in which the way a rotating star's absorption lines shift as different parts of the surface move toward and away from the observer, is used to reconstruct the temperature map of the full surface. A large BY Draconis star can be seen to carry a dark region covering 15 or 20% of one hemisphere, deep and cool against the surrounding orange, rotating steadily into view and then out again with each turn of the star. The period of the brightness variation is exactly the rotation period of the star. There is no other source. A single feature, dark and wide, turning on its axis, makes the star appear to rise and fall in measured steps. The light curve of a BY Draconis variable is not a sharp dip like Algol's eclipse. It is a broad, shallow wave, a slow rise, a slow fall, a minimum that is rounded rather than flat, shaped by the fact that a round star spot on a round star does not block light with a sharp edge. As the spot approaches the limb of the star on one side, it begins to contribute less, both because it covers less of the visible area and because light from the limb of a star is naturally dimmer than light from the center of the disk. When the spot is centered, the dimming is deepest. As the spot moves away, the brightness slowly returns, and then the star, if the spots are confined to one region, stays at its resting brightness until the next rotation brings the spot around again. Over years, the amplitude of this wave changes. The spots grow and decay, as sunspots do. New spot groups form in different latitudes, shifting the phase of the light curve. In some active periods, the star is more heavily spotted. The amplitude, the range between the bright maximum and the dim minimum, grows. In quieter periods, the amplitude shrinks. This long rise and fall of spot activity, traced across a decade of photometric measurements, echoes in a more extreme and vivid register the sun's own 11-year cycle. The cycle in some BY Draconis stars is longer, and in some shorter, and in some not clearly periodic at all, a waxing and waning of magnetic activity that the stars share in common without being synchronized with each other or with the sun. The RS Canum Venaticorum stars carry this to a further degree. RS Canum Venaticorum itself, the name comes from a binary star in the constellation of the hunting dogs, the pair of hounds that follows the Great Bear across the northern sky, is a close pair in which at least one component is a late-type giant, a star cooler and larger than the sun, locked in rapid rotation by the tidal pull of its companion. Tidal synchronization is the process. When two stars are close enough, the gravitational bulge each raises on the other acts as a brake, gradually slowing or speeding each star's rotation until the rotation period matches the orbital period exactly. The way the moon's rotation has been locked to its orbit so that the same face always points toward Earth. A giant star rotating in a matter of days, synchronized with a close orbital companion, develops magnetic activity on a scale that dwarfs what the sun produces. Star spot groups in RS Canum Venaticorum systems can cover up to 30% of the visible surface. Dark, cool regions, so extensive that the brightness change they produce as the star rotates is immediately apparent in even casual observations. The light curve amplitude, the peak to trough difference in brightness over one rotation cycle, can reach half a magnitude or more. These are not subtle variations. They are unmistakable, visible in small telescopes, changing from one year to the next as the spot distribution shifts. The long-term record of an RS Canum Venaticorum system, observed across many years, shows the same cyclical behavior as a BY Draconis star, but in a more pronounced key. The amplitude rises over several years as spot coverage increases, reaches a rough maximum, and then gradually falls as the magnetic activity subsides and the spots dissipate before the cycle turns again. The length of these activity cycles, measured in light curves rather than in direct sunspot counts, typically runs from a few years to a few decades, a range that brackets the sun's own cycle comfortably on both sides. In studying these stars, the sun's quiet oscillation between more and fewer spots, between more and less activity, is not a peculiarity of one middle-aged yellow dwarf. It is a pattern that runs across the sky, expressed in cooler stars, in faster rotators, in pairs too close to be resolved by any eye. An ellipsoidal variable offers a gentler version of this geometry without the drama of eclipses or the activity of star spots. In a system of this kind, at least one of the two stars has been tidally distorted into an elongated shape, its surface pulled toward the companion, but the orbital plane is tilted just enough that the two stars never cross each other's faces, as seen from Earth. No eclipse occurs, no blocking of light happens at any orbital phase, and yet the star varies because the shape of the distorted body changes how much surface the observer sees as it orbits. The smooth, double-humped light curve of an ellipsoidal variable carries two maxima and two minima per orbit. When the long axis of the tidally stretched star is presented broadside, when the observer sees the greatest extent of the elongated face, the brightness is at its highest. A quarter orbit later, the long axis points toward the observer, and the projected surface area is at its minimum. The brightness falls. Another quarter orbit, and the broadside face returns. The brightness rises again. Then the minimum again, and the cycle continues. 2 complete peaks and 2 complete valleys for every single trip around the orbital path. No eclipse, no star spot, no pulsation, only the changing shape of a surface as it turns. The light curve of an ellipsoidal variable is one of the most regular and featureless in the whole catalog of variability. It does not have the sharp transitions of an eclipsing binary. It does not have the slow asymmetric rise and fall of a pulsating giant. It does not have the modulated amplitude of a spotted rotator. It is a pure, smooth geometric wave, the kind of curve a textbook might draw to illustrate a simple oscillating function. And in its smoothness, in its perfect periodicity, in the total absence of anything sudden or unexpected, it rests. It simply continues, orbit after orbit, the stretched star turning its faces toward the observer and away, the light rising and falling in a wave that has no beginning anyone alive remembers, and no end anyone alive will see. What all of these systems share, the eclipsing pair, the distorted contact binary, the spotted rotator, the tidally stretched ellipsoidal, is that the variability belongs to the geometry, not to the stars. A perfectly constant star in the right orbital alignment would show up in any brightness survey as a variable. A perfectly quiet star carrying a large dark spot on one hemisphere would look to a distant observer like a star rhythmically dimming and brightening. The variability is not inside the star. It is in the arrangement, in the angle, in the surface pattern, in the relationship between the direction the observer happens to be standing and the direction the physics of the system happens to be pointing. This is a different kind of revelation from the one pulsating stars offer. A Cepheid speaks from within, the whole body of the star expanding and contracting, driven by processes buried in the helium ionization zone, invisible and deep. A Mira speaks from within, the vast envelope stirring and stirring again, losing its outer layers to the dark and slow clouds. but an eclipsing binary speaks from its geometry. The star itself may be entirely still. What the observer reads in the light curve is the architecture of the system, the inclination of the orbit, the sizes and temperatures of the two components, the distance between them, the presence of a disk or a spot. All of this is encoded in the shape of the curve. A light curve is an address. An eclipsing binary's light curve contains the depth of the primary eclipse, the depth of the secondary eclipse, the duration of each, the shape of the ingress and egress, as one disk slides across another, and the shape of the intervals between. From those measurements alone, from those quiet marks on a graph, the ratio of the stellar radii, the ratio of their surface brightnesses, and the inclination of the orbit can be calculated. If a radial velocity curve is added, built from the Doppler shifts in the spectrum as the stars move toward and away from the observer throughout their orbit, then the actual masses and actual radii of both stars emerge. In no other way can a star's mass and radius be determined simultaneously and directly from observation. Eclipsing binaries are the physical calibration points for everything else understood about stellar structure. An RS Canum Venaticorum star passes one additional message. Its light curve changes from year to year as the spot pattern shifts, and in that change the star's long-term magnetic cycle is written. If the activity cycle runs 15 years, then 15 years of photometry will show one full rise and fall of amplitude. The timing of the light curve maximum relative to the orbital phase will shift as the dominant spot group migrates in longitude across the stellar surface. These migrations are analogous to the drift of sunspot groups toward the equator as the solar cycle progresses, a pattern called Spur's law on the sun, and present in faint echo in the light curves of distant stars, too small to resolve into a surface directly. In those long records, stretching across a decade or two of careful measurement, the sun appears in a new light, not as a special case, not as the only star of its kind, but as one instance of a pattern that is common and old and quiet. The sun spots, its cycle, its slow waxing and waning of magnetic activity. These are not unusual. They are the natural consequence of a convective outer envelope rotating and developing a dynamo, and they belong to every cool star with a similar structure, from the faintest M dwarfs to the RS Canum Venaticorum giants, with their hemisphere spanning dark regions. There is something in this that is slow to arrive, but once arrived, rests easily. The sky, which looks still on any given night, is full of motion that the eye cannot resolve in a single evening. Stars dimming in eclipse, stars carrying their spots around, stars stretched by a neighbor, turning their elongated faces toward the observer as they orbit. The stillness of the sky is the stillness of the human timescale, not of the sky itself. Given months, given years, given the patience that a light curve requires, which is the patience of many evenings, of small consistent efforts, of returning to the same star night after night and writing down a single number, the sky reveals itself to be in constant, varied, quiet motion. The Algol system has been dimming and brightening on its nearly 3-day cycle for a time that vastly exceeds any human measure of attention. Long before Goodricke held his pen to paper on a cold night in York, the geometry of that system was producing exactly the same dip, the same recovery, the same secondary minimum, 12 hours after the deep eclipse. The stars have not changed in any way that matters on the timescale of a human life. The orbit has not shifted. The inclination has not tilted. The same clockwork that Goodricke measured in 1782 runs tonight as he measured it, and will run for millions of years after the last record of his observation has dissolved. The spotted dwarfs carry their dark regions through rotations that, in the most rapidly spinning examples, run only a day or two. A star rotating once every 2 days makes roughly 180 turns in the span of a single Earth year, and its spot pattern traces through that many cycles, each one recorded if there is someone at the telescope each night to see it. The amplitude of the BY Draconis wave stays roughly the same through a quiet period, then slowly rises as new spots form, then falls as they dissipate. The pattern shifts. The star's activity is changing on its own clock, independent of anything else. In an RS Kanama Venaticorum system, that activity cycle might run 10 years. The amplitude that a photometrist measures in the first year of a monitoring campaign might be small, spots modest in size, the wave in the light curve shallow and barely rising above the noise. By the 5th year, the amplitude might have grown significantly, the spots now large and prominent, the wave in the light curve clearly visible. By the 10th year, the activity might be subsiding again, the amplitude shrinking, the spotted hemisphere clearing, and the star settling toward the same quiet minimum it started from before the cycle turns once more. A researcher who begins such a campaign is committing to a decade of patience. Many such campaigns have been running since the 1970s. They are still running. The stars have not finished their cycles. Some have completed 1, some have completed 2. The records accumulate, rows of measurements, nightly or weekly, the brightness at this particular Julian date, the comparison, star's brightness noted alongside, the atmospheric conditions noted in a separate column. And from those rows, slowly, the shape of the cycle emerges, the way a coastline emerges on a long voyage, detail appearing gradually out of what was first only an undifferentiated horizon. There is no equivalent of a finished picture. The sky is not a problem to be solved. A light curve extended by another year is a year more of information, and that year might be the year in which the activity cycle turns, or the year in which the spot group migrates to a new longitude and shifts the phase of the wave, or simply another year in the long flat minimum that precedes a rise no one has yet seen coming. The observer does not know which it will be. The record continues regardless. On a quieter night, in a constellation few people learn by name, a small ellipsoidal binary moves through its orbit without anyone watching. The tidally stretched component turns its broad face toward the zenith, then rotates away, the brightness climbing and falling in its smooth geometric wave, the curve rising to its small maximum and settling to its small minimum in a few hours, and then rising again. No one is measuring it on this particular night. The brightness is changing anyway. It has been changing this way for as long as the system has been in its current configuration, which is older than any instrument used to measure it, and it will continue changing this way long after the measurement campaigns that first cataloged it have ended and the notes from those campaigns have been transferred to formats that no longer exist. The pattern does not require a witness. It proceeds in the dark crash, in the geometry of two bodies moving around a common center, in the tidal bulge that one raises on the surface of the other, in the slight excess of light when the broad face presents itself, and the slight reduction when the narrow end points toward the observer's empty sky. The Baba Draconis star in Draco, the one that gave its name to an entire class of variable, carries its spots through another rotation tonight, as it has for all the years since its variability was first cataloged. The dark region on its surface is roughly where it has always been in its slow migration. Its amplitude is neither at its maximum nor its minimum in the long activity cycle, but somewhere in the long middle of the rise or the fall, the kind of middling moment that characterizes most of any cycle, where the change is real but unhurried and requires more than a single season to discern. In that slow middle, in the unhurried passage through the middle of a cycle that began before anyone measuring it was born, there is an image that holds something of what the whole catalog of extrinsic variability contains. The star is not changing, its fusion rate is not fluctuating, its radius is not oscillating, its companion is not crossing its face. What is changing is the pattern of magnetism on its surface, the distribution of dark regions, the proportion of the hemisphere that is covered in spots, and that change is itself the product of a deep, slow process inside the star, a magnetic dynamo driven by the interaction of convection and rotation, a process that has analogs in the sun and in every other star cool enough to convect and old enough to have settled into a rhythm. The spots are a surface expression of something internal. They are not the interior, but they are its fingerprint. And the light curve, that long, patient record of small brightness values gathered night after night across years, is the paper that holds the fingerprint. From the curve alone, without ever being close to the star, without any instrument that could resolve the surface into a visible image, the presence of the spots, their size, their position, their evolution, can be inferred. The star speaks through its light, and the light is changed by what is on the surface, and the surface is shaped by what is inside, and what is inside is the same physics that the sun practices quietly each cycle, the same physics that produced the Maunder minimum in the 17th century, when sunspots nearly vanished for 70 years, and the winters grew colder, the same physics that will produce future cycles with characteristics not yet known. The Algol system, somewhere above the horizon tonight in the autumn sky, is moving through the long middle of an orbit that has no beginning anyone witnessed. The cool giant is perhaps a quarter of the way through its passage across the face of the blue-white companion, the eclipse not yet at its deepest, the light curve still descending toward its minimum, or the eclipse has ended and the curve is rising back toward the flat interval of full light, or the secondary eclipse is approaching, the giant beginning to pass behind the companion, not blocking its light now, but having a portion of its own dimmer light blocked for a few hours. One of these is true at this moment, and none of them is known to anyone who is not at a telescope. By morning, the system will be in a different phase. By next week, it will have completed roughly 2 full orbits. In a year, it will have completed more than 100. The dimming will have happened, and the recovering will have happened more than 100 times in the span of a single year. And most of those dimmings will have passed without observation, in daylight, in cloudy weather, in the ordinary unmeasured hours when no one is watching the particular degree of sky where Perseus rises. The curve does not need to be watched continuously to be understood. It only needs to be sampled consistently, patiently, over a long enough baseline, and the shape that emerges from even sparse, irregular measurements is sufficient to determine the period, the depth, the orbital inclination, the stellar radii. The star is generous with its information. It encodes everything in the light. The light is always there. The measuring is what is intermittent. On the longest timescales that photometric monitoring campaigns have tracked, 30 years, 40 years, for the handful of systems that have been followed without interruption, the stars have shown that even their activity cycles have cycles. An Rs Canum Venaticorum star that was observed for 2 decades showed a clear activity cycle of roughly 12 years. But the 2 cycles observed were not identical. The second was slightly shorter. The amplitude of the spots was slightly higher. Whether this represents a long-term trend, a drift in the underlying cycle length, or simply the natural variation of a process that is periodic but not perfectly clock-like, No one knows yet. The data continues to accumulate. The answer, if there is a clean one, is still in the future of the record. For now, the light curves rest in archives, long columns of numbers. The brightness of a particular star on a particular date, recorded in a unit that relates to the human eye's perception of stellar light. A unit whose scale was set by astronomers in Alexandria 2,000 years ago and refined to its current precision over the centuries since. Magnitudes. A difference of 5 magnitudes is exactly a factor of 100 in brightness. A difference of 1 magnitude is a factor of about 2.5. The smallest difference the eye can reliably detect under good conditions is about 1/10 of a magnitude. The smallest difference modern photometers can measure is 1,000 times finer than that. Between those two thresholds, what the eye can just barely see and what the best instruments can reliably measure, lies the full range of extrinsic variability. Some eclipsing binaries dip by 4 or 5 magnitudes at primary minimum. Some ellipsoidal variables wave by only a few hundredths of a magnitude, detectable only because the instruments are so sensitive. Some spotted dwarfs modulate by half a magnitude. Some RS Canum Venaticorum stars swing through a full magnitude or more at their most active. The sky contains all of these simultaneously and has always contained them, and on any given clear night, all of them are cycling through their current phases, with no attention paid and no record taken. The record is not the phenomenon. The phenomenon is older and indifferent. The orbit of the Algol system predates the existence of the solar system. The magnetic cycles of the spotted dwarfs are older than any technology capable of measuring them. The smooth wave of the ellipsoidal binary rises and falls in an empty sky that has been empty of observers for most of its existence and will be empty again. The record is a thin layer of human attention laid over something that proceeds with or without it. What matters, what the patient accumulation of measurements has revealed, is that brightness is not a fixed property of a star. It is a variable. It changes because a companion crosses the face, because a tidally stretched body presents its different aspects, because a dark spot rotates in and out of view, because the magnetic cycle that drives the spots rises and falls on its own long time scale, because the orbit of a distorted pair produces 2 small maxima and 2 small minima in a perfectly smooth perpetual wave. The causes are different. The mechanism in each case is different, but the result is the same: a light curve, a graph, a long patient record of small numbers that together trace the shape of something real. The light from Algol that reaches the eye tonight left the system some 90 years ago. The eclipse being observed now happened in the early decades of the 20th century, when the photometric technology used to record it had not yet been invented. The system was already in that orbit then. The same geometry, the same plane, the same clock. The light traveling across those 90 light years carries the information of a dip that no one measured at the time it occurred, arriving now to be measured or to pass unmeasured through a clear sky where the only instrument is an eye that does not know to look for it, across the whole sky. On this same night, thousands of extrinsic variables are in the middle of their current cycles. Some are in eclipse, some are presenting their broadest faces, some are carrying large spot groups through the center of the visible disk, dimmed and slow. Some are in the long flat interval between eclipses, bright and steady, giving no sign of what will happen in a few hours when the orbit brings the companion back across the line of sight. They proceed in silence, in the old arrangement of masses and distances and orbital inclinations that has governed each system since it formed, and they will continue long past the last measurement, long past the last language capable of recording one, long past the fading of the smallest light in the sky. The spotted star in Draco has turned a little further in its rotation since this began. The dark region at the center of the visible hemisphere is drifting toward the limb now. Slowly, the way a cloud drifts across a sky when there is no wind to notice. The light is increasing almost imperceptibly as the cooler spot moves toward the edge and the brighter photosphere opens behind it. By morning, the spot will be nearer the limb,